Deep in the lowland jungles of the Yucatan Peninsula, buried under centuries of tropical vegetation, stand the ruins of cities that were built from a material the modern world is only beginning to understand. The temples of Tikal, rising above the canopy like stone mountains. The palace complexes of Palenque, their corbelled vaults still intact after 13 centuries of monsoon rains and root infiltration. The Great Pyramid of Calakmul, its core a solid mass of rubble and binding agent that has withstood earthquakes, hurricanes, and the relentless chemical assault of one of the most corrosive environments on the planet, the tropical rainforest. These structures were not built from cut stone alone. They were built using a cementitious material, a form of concrete that the ancient Maya developed independently from any old world tradition, and that possesses properties the modern construction industry is only now learning to appreciate. The Maya did not have the wheel, they did not have iron tools, they did not have draft animals, they did not have the arch, and yet they built cities that housed tens of thousands of people, constructed pyramids that reached heights of 70 meters, and engineered water management systems that sustained dense urban populations in an environment with a 6-month dry season. They accomplished these feats using a material that was produced from limestone, the bedrock of the Yucatan itself, burned in open kilns, slaked with water, and mixed with aggregates to form a binding agent that held their cities together for more than a millennium. The material has no universally agreed upon name. Some scholars call it Maya concrete, others call it Maya lime plaster, or Maya stucco. Others prefer the term lime-based cementitious material. The terminology varies, but the substance does not. It is a lime-based binding material that was used in quantities that are difficult to comprehend, covering the floors, the walls, the roofs, the plazas, the roads, and the water reservoirs of every major Maya city, forming a continuous waterproof skin that protected the stone structures beneath it, and that gave the Maya cities their distinctive, gleaming white appearance. The scale of the Maya concrete production was enormous. The city of El Mirador, which flourished in the pre-classic period around the 6th century before the Common Era, contains structures whose cores are composed of an estimated million cubic meters of fill material bound by lime concrete. The production of this quantity of concrete required the burning of millions of tons of limestone, a process that consumed vast quantities of fuel wood and that may have contributed to the deforestation that some scholars believe played a role in the collapse of several Maya cities. The Maya concrete industry was, by any measure, one of the largest construction material industries in the pre-Columbian Americas, and the material it produced was the foundation, both literally and figuratively, of one of the most sophisticated civilizations in the ancient world. By the end of tonight, you are going to understand what Maya concrete was, how it was made, what properties it possessed that allowed it to endure for over 1,000 years in one of the most destructive environments on the planet, and what modern science has discovered about the specific chemistry that makes this ancient material so remarkable. You are going to learn about the specific techniques the Maya used to produce their concrete, the specific additives they incorporated to enhance its performance, and the specific ways in which their material differs from, and in some respects surpasses, the concrete of the Romans and the cement of the modern world. And you are going to confront a question that connects the Maya achievement to the most urgent challenges of modern construction. Can this ancient material teach us how to build a more sustainable future? Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The Maya concrete has been hiding in plain sight for centuries. Every archaeologist who has excavated a Maya site has encountered it. Every tourist who has climbed the steps of Chichen Itza has walked on it. Every photograph of a Maya ruin shows it, the white surfaces, the plastered walls, the thick floors of the plazas. But the material itself, its chemistry, its engineering, its remarkable durability, has only recently become the subject of the systematic scientific investigation that it deserves. The story of how this investigation has unfolded and what it has revealed is one of the most fascinating chapters in the archaeology of ancient materials. Now, let us begin. the comparison with Roman concrete is inevitable and instructive. The Romans, as we explored in a previous episode, developed a volcanic ash concrete that has survived for 2,000 years, and that possesses specific self-healing properties that the modern construction industry is struggling to replicate. The Maya, working on the opposite side of the world, with no contact with the Roman tradition and no access to volcanic ash, developed a lime concrete that has survived for over 1,000 years in conditions that are far more destructive than the Mediterranean environment in which the Roman concrete was developed. The convergence is striking. Two civilizations, separated by an ocean and by more than a millennium, each developed a cementitious material of extraordinary durability, each using the specific resources that their environment provided, each solving the specific problems that their environment posed. The convergence suggests that the development of durable concrete is not a unique achievement of any single civilization, but a recurring pattern in the history of human technology, a pattern in which the specific demands of the environment drive the specific development of the materials that are needed to meet those demands. The question of how the Maya achieved this level of materials engineering without the formal scientific knowledge of modern chemistry and modern materials science is one of the most profound questions in the study of ancient technology. The Maya did not know the chemical formulas. They did not know the names of the specific compounds that were formed during the production of their concrete. They did not possess the analytical instruments that would have allowed them to observe the microstructure of the material or to measure its specific mechanical properties. And yet they produced a material that has properties which modern materials scientists, working with the full resources of modern analytical chemistry and modern engineering, have only recently been able to identify and to explain. The gap between the Maya craftsmen's lack of formal knowledge and the sophistication of the material they produced is one of the most humbling gaps in the history of human technology. To understand Maya concrete, we must first understand the civilization that produced it and the specific environmental conditions that shaped its development. The Maya civilization, which flourished in the lowlands of southern Mexico, Guatemala, Belize, Honduras, and El Salvador over a period of approximately 3,000 years, was one of the most intellectually and architecturally sophisticated civilizations in the pre-Columbian Americas. The Maya developed a fully literate culture with a complex writing system, a calendar of extraordinary mathematical precision, an advanced astronomical tradition that could predict eclipses and planetary movements, and an architectural tradition that produced some of the most impressive structures in the ancient world. The geological foundation of the Maya lowlands is limestone, a sedimentary rock composed primarily of calcium carbonate that was deposited by ancient seas over millions of years, and that now forms a flat, porous platform that underlies the entire Yucatan Peninsula. The limestone bedrock of the Yucatan is the key to understanding Maya concrete, because limestone is both the construction material from which the Maya buildings were built and the raw material from which the Maya concrete was produced. The Maya lived on limestone, built with limestone, and made their concrete from limestone. And the specific properties of the Yucatan limestone, its chemical purity, its relative softness when freshly quarried, and its ready availability at every construction site, shaped every aspect of the Maya construction tradition. The specific chemistry of limestone is essential for understanding the production of Maya concrete. Limestone is composed primarily of calcium carbonate, a chemical compound with the formula that chemists write as calcium carbonate. When limestone is heated to a temperature of approximately 800 to 900 degrees Celsius, the calcium carbonate decomposes in a chemical reaction known as calcination, releasing carbon dioxide gas and leaving behind a white powder known as quickite or calcium oxide. When the calcium oxide is mixed with water, it undergoes a violent exothermic reaction known as slaking, absorbing the water and producing a paste known as slaked lime or calcium hydroxide. The slaked lime paste, when applied to a surface and allowed to dry, gradually absorbs carbon dioxide from the atmosphere and reconverts to calcium carbonate, the same chemical compound from which it was originally derived, in a process known as carbonation. The carbonation process, which can take months or years to complete, produces a hard, durable material that is chemically identical to the original limestone, but that has been reformed into a new shape, binding together the aggregate particles and the structural elements with which it has been mixed. The lime cycle, as this sequence of calcination, slaking and carbonation is known, is the fundamental chemical process that underlies the production of all lime-based construction materials, including the lime mortars and plasters of the ancient Near East, the lime concrete of the Romans, and the lime concrete of the Maya. The lime cycle was discovered independently by multiple civilizations in different parts of the world, and the Maya discovery of the lime cycle, which appears to have occurred in the pre-classic period, approximately 2,000 years before the Common Era, was one of the foundational innovations of the Maya construction tradition. The specific conditions of the Maya lowlands, which include a tropical climate with high temperatures, high humidity, and a pronounced wet-dry seasonality, posed specific challenges for the production and the use of lime concrete that were different from the challenges faced by the lime producers of the ancient Mediterranean. The high temperatures of the tropical climate accelerated the setting and the drying of the lime concrete, requiring the Maya to work quickly and to manage the water content of their mixes with precision. The high humidity of the tropical climate affected the rate of carbonation, slowing the process in the wet season and accelerating it in the dry season. The alternating wet and dry seasons subjected the concrete to repeated cycles of wetting and drying that could damage the material if it was not properly formulated and properly applied. The fuel requirements of the lime production process were another specific challenge that the Maya faced. The calcination of limestone requires temperatures of approximately 800 to 900 degrees Celsius, which must be maintained for a period of several hours to ensure the complete conversion of the calcium carbonate to calcium oxide. The fuel that the Maya used for the calcination was wood, the only fuel that was available in the tropical lowlands, and the consumption of wood for lime production was enormous. The estimates of the wood consumption for the production of the lime concrete used in a single major construction project, such as the construction of a large pyramid, run into the tens of thousands of cubic meters, quantities that would have required the clearing of substantial areas of forest. The environmental impact of the Maya lime production has been the subject of considerable research and debate among archaeologists and environmental scientists. Some scholars have argued that the deforestation caused by the lime production, combined with the deforestation caused by agriculture and by the production of fuel for domestic use, was a significant factor in the environmental degradation that is believed to have contributed to the collapse of several major Maya cities in the 9th century of the Common Era. The argument is that the Maya, by consuming vast quantities of wood for the production of lime concrete, reduced the forest cover of the lowlands to a point where the soils were exposed to erosion, the water cycle was disrupted, and the agricultural productivity of the land was diminished, creating a cascade of environmental problems that undermined the economic and the social foundations of the Maya cities. The counter-argument is that the Maya were sophisticated environmental managers who understood the relationship between their resource consumption and the health of the environment, and who developed strategies for the sustainable management of their forest resources. The evidence for this counter-argument includes the identification of specific tree species, such as the ramon tree, that were cultivated by the Maya for their fruit, their wood, and their use as a fuel source, and the archaeological evidence of managed woodlands and of the selective harvesting of wood that minimized the impact of the fuel consumption on the forest ecosystem. Specific kilns that the Maya used for the calcination of limestone have been the subject of archaeological investigation, and the remains of Maya lime kilns have been identified at several sites across the Maya lowlands. The kilns were typically simple, open structures, either pits dug into the ground or raised platforms of stone, in which layers of limestone and wood were stacked alternately, and the wood was set alight, producing a fire that was hot enough and sustained enough to convert the limestone to quick lime. The simplicity of the Maya kilns which contrasts with the more elaborate shaft kilns and draw kilns that were used in the Old World lime industry, reflects the specific conditions of the Maya lowlands, where the availability of fuel and the properties of the local limestone favored a simpler, more labor-intensive approach to lime production. The specific question of at what temperature the Maya kilns operated has been addressed by researchers who have analyzed the composition of Maya lime products using X-ray diffraction and other analytical techniques. The analyses have revealed that the Maya lime was typically produced at temperatures that were lower than the temperatures used in modern lime production, approximately 750 to 850 degrees Celsius, rather than the 1000 degrees Celsius or more that is typical of modern kilns. The lower production temperature has significant implications for the properties of the resulting lime, because the calcium oxide that is produced at lower temperatures is more reactive and more easily slaked than the calcium oxide that is produced at higher temperatures, and the lime putty that is produced from the lower temperature quicklime has specific properties, including a finer particle size and a higher surface area, that affect the performance of the concrete. The slaking process, in which the quicklime is mixed with water to produce the lime putty that is the binding agent of the concrete, was another stage of the production process that the Maya managed with specific skill and specific care. The slaking of quicklime is an exothermic reaction that produces a large amount of heat, and the management of this heat, which can cause the mixture to boil and to spatter if it is not controlled, requires the careful addition of the water and the continuous stirring of the mixture. The Maya slaking process appears to have been conducted in pits or in large vessels, and the lime putty that was produced was often aged for a period of days, weeks, or even months before it was used, a practice known as lime putty aging that improves the workability and the performance of the lime by allowing the calcium hydroxide crystals to grow and to develop a more uniform structure. The aggregates that the Maya added to the lime putty to produce their concrete included crushed limestone, which provided bulk and reduced the shrinkage of the material as it dried, and a variety of organic and mineral additives that served specific purposes, including the improvement of the workability, the enhancement of the durability, and the modification of the setting time. The specific additives that the Maya used and the specific purposes that they served have been the subject of extensive research that has revealed a level of materials engineering sophistication that was not expected and that has transformed the understanding of the Maya construction tradition. The specific social organization of the Maya construction industry, which has been inferred from the archaeological evidence of the construction sites and from the ethnographic evidence of the modern Maya communities, was a critical factor in the production and the application of the Maya concrete. The Maya construction industry was organized on a communal basis, with the labor for the construction of the public buildings, the temples, the palaces, and the plazas being provided by the commoners as a form of tribute or of community service, organized and directed by the elite classes who controlled the political and the religious institutions of the Maya state. The specific labor requirements of the concrete production, which included the quarrying of the limestone, the gathering of the fuel wood, the burning of the kiln, the slaking of the quicklime, the mixing of the concrete, and the application of the concrete to the surfaces, were substantial, and the coordination of these activities required a level of organizational capability that speaks to the sophistication of the Maya administrative system. The estimates of the labor that was required for the production of the lime concrete used in a single major construction project, such as the construction of a large pyramid, suggest that hundreds of workers were involved in the concrete production alone, working in coordinated teams that performed the different stages of the production process in a specific sequence and at a specific pace. The specific knowledge of the concrete production, which included the knowledge of the specific temperatures, the specific materials, the specific proportions, and the specific procedures that were needed for the production of a high-quality material, was concentrated in the hands of a relatively small number of specialist craftsmen, the master builders, who directed the work of the larger labor force, and who were responsible for the quality of the finished product. The master builders, who were members of the Maya elite or of a specialized class of craftsmen that occupied a specific position in the Maya social hierarchy, possessed the specific knowledge that was needed for the production of the different types of concrete that were used in the different applications, and the transmission of this knowledge from one generation of master builders to the next was one of the most critical elements of the Maya construction tradition. The ethnographic evidence from the modern Maya communities provides specific information about the traditional methods of lime production that have been maintained by the indigenous craftsmen, and that may reflect the ancient production methods with considerable fidelity. The modern Maya lime producers, who are known as caleros, produce quick lime in open kilns that are similar in their basic design to the kilns that have been identified at ancient Maya sites, and the specific procedures that they follow for the burning, the slaking, and the mixing of the lime are consistent with the procedures that have been inferred from the archaeological evidence. The collaboration between the modern researchers and the caleros has been one of the most productive aspects of the Maya concrete research, because the caleros possess specific practical knowledge about the behavior of the lime at different stages of the production process that is not available from any written source, and that provides essential context for the interpretation of the archaeological evidence. The specific evidence for the scale of the Maya lime production comes from the archaeological analysis of the structures themselves, which allows the estimation of the quantity of concrete that was used in each structure and the calculation of the quantity of limestone and of fuel wood that would have been required for the production of that concrete. The city of El Mirador, which was one of the largest Maya cities of the pre-classic period, and which contains some of the most massive structures in the Maya world, including the Ladanta Pyramid, which is one of the largest pyramids by volume in the ancient world, provides a specific case study of the scale of the Maya concrete industry. The Ladanta Pyramid at El Mirador, which rises to a height of approximately 72 meters above the plaza level, and which has a total volume of approximately 2.8 million cubic meters, is composed primarily of a rubble core that is bound by lime concrete. The quantity of lime concrete that was used in the construction of the pyramid has been estimated at approximately 100,000 to 200,000 cubic meters, a quantity that required the calcination of approximately 200,000 to 400,000 tons of limestone, and the consumption of approximately 400,000 to 800,000 cubic meters of fuel wood. The production of this quantity of lime concrete, which would have been spread over a construction period of decades or centuries, represents an enormous investment of labor and of natural resources that speaks to the specific importance that the Maya placed on the construction of their monumental architecture, and to the specific organizational capability that the Maya state possessed for the mobilization and the coordination of the labor and the resources that were needed. The specific question of how the Maya managed the fuel supply for their lime production has been addressed by environmental archaeologists who have studied the pollen records, the charcoal remains, and the soil chemistry of the Maya lowlands for evidence of the specific patterns of forest management that the Maya practiced. The evidence suggests that the Maya managed their forests through a combination of selective harvesting, in which specific trees were chosen for cutting based on their species, their size, and their location, and of managed regrowth, in which the harvested areas were allowed to regenerate over a period of years before being harvested again. The specific tree species that were favored for fuel wood include the species that produce a hot, sustained flame when burned, such as the logwood and the sapodilla, and the species that regenerate quickly after cutting, such as the various pioneer species that colonize the cleared areas of the tropical forest. The specific chronological development of the Maya concrete tradition provides essential context for understanding the specific achievements of the tradition at different periods. The earliest evidence of lime production in the Maya lowlands dates to the Middle Preclassic period, approximately 1,000 years before the Common Era, when the first small-scale structures were built using a simple lime mortar that was used to bind the stone blocks of the walls and the platforms. The early lime mortar was a relatively simple material, produced from quicklime that was mixed with water and with crushed limestone aggregate, without the specific organic additives that would characterize the later Maya concrete. The transition from the simple lime mortar to the more sophisticated lime concrete occurred during the late Preclassic period, approximately 400 years before the Common Era to 250 years of the Common Era, when the Maya began to build the large-scale monumental structures, the pyramids, the temples, and the palaces that required a more durable and a more workable material than the simple lime mortar. The specific innovations that characterize the late Preclassic concrete include the introduction of the organic additives, the development of the specific mixing and application techniques that produced a more uniform and more durable material, and the development of the specific formulations for the different applications, including the structural fill, the floor paving, and the stucco. The Classic period, approximately 250 to 900 of the Common Era, represents the peak of the Maya concrete tradition, when the most sophisticated formulations were developed and when the most elaborate structures were built. The Classic period concrete, which has been analysed in detail from sites across the Maya lowlands, shows the highest concentrations of organic additives, the most compact microstructures, and the best mechanical properties of any Maya concrete, reflecting the specific investment of knowledge and of skill that the Classic period master builders brought to the production of the material. The post-Classic period, approximately 900 to 1520 of the Common Era, marks the beginning of the decline of the Maya concrete tradition, as the abandonment of the major Classic period cities and the disruption of the social structures that had sustained the tradition led to a progressive simplification and deterioration of the concrete production. The post-Classic concrete, which has been analysed from sites in the northern Yucatan and in the Guatemalan highlands, shows lower concentrations of organic additives, simpler microstructures, and lower mechanical properties than the Classic period concrete, reflecting the specific loss of the advanced knowledge that had characterized the tradition at its peak. The specific observation that the Maya concrete tradition showed a trajectory of progressive improvement over approximately 1,500 years, from the simple lime mortar of the Middle Preclassic to the sophisticated engineered concrete of the Classic period, provides evidence for the specific process by which the tradition developed. A process of incremental improvement through empirical observation and intergenerational transmission, in which each generation of builders built on the specific knowledge of the previous generation and added its own specific innovations to the tradition. The specific water management implications of the Maya concrete deserve additional examination, because the management of water was the central engineering challenge that the Maya faced, and because the Maya concrete was the specific material that made the solution of this challenge possible. The Maya lowlands, which occupy a flat, porous limestone platform with very few surface rivers and no permanent lakes, presented the Maya with a specific and urgent water management problem: how to collect, store, and distribute the rainwater that fell during the 6-month wet season so that the population could survive through the 6-month dry season. The solution that the Maya developed was a comprehensive water management system that included the collection of rainwater from the roofs and the plazas of the city, the channeling of the collected water through a network of drainage channels and settling tanks, and the storage of the water in large, plastered reservoirs that were lined with waterproof Maya concrete. The specific engineering of the Maya water reservoirs has been studied in detail at several sites, including the sites of Tikal, Calakmul, and Uxmal, and the investigations have revealed a level of hydraulic engineering sophistication that is comparable to the hydraulic engineering of the ancient Romans. The reservoirs at Tikal, which have been the subject of the most detailed investigation, consisted of a series of interconnected basins that were carved into the bedrock and lined with multiple layers of lime concrete, each layer approximately 5 to 10 centimeters thick, to produce a waterproof barrier that prevented the stored water from seeping into the porous limestone below. The total storage capacity of the Tikal reservoir system has been estimated at approximately 100,000 cubic meters, a quantity that was sufficient to sustain a population of approximately 40 to 60,000 people through the dry season. And the engineering of the system, including the design of the catchment areas, the grading of the drainage channels, the sizing of the settling tanks, and the waterproofing of the reservoir linings, demonstrates a comprehensive understanding of the principles of water management that is one of the most impressive engineering achievements of the pre-Columbian Americas. The specific question of how the Maya achieved the waterproofing of the reservoir linings, which had to be completely impermeable to water to prevent the loss of the stored water through seepage, has been addressed by the analysis of the specific concrete that was used in the reservoir applications. The analysis has revealed that the reservoir concrete contains the highest concentrations of organic additives of any Maya concrete, with the chucum extract and the opal mucilage present in concentrations that are significantly higher than the concentrations found in the structural and the paving concretes. The high concentrations of organic additives produce a concrete with an exceptionally low water absorption rate, typically less than 5% by weight, a value that is comparable to the water absorption rate of modern waterproof concrete, and that is sufficient to prevent significant seepage through the reservoir lining. The specific relationship between the Maya concrete tradition and the Maya architectural tradition deserves additional examination, because the specific properties of the Maya concrete shaped the specific forms of the Maya architectures in ways that are not always appreciated. The Maya architectural tradition, which is one of the most distinctive and the most visually impressive in the ancient world, is characterized by specific features that are directly related to the specific properties of the lime concrete that was used in the construction, including the corbelled vault, the massive wall, the steep pyramid profile, and the thick floor surface. The corbelled vault, which is the most distinctive structural feature of Maya architecture, and which was the only spanning technique that the Maya used for the roofing of interior spaces, is a specific response to the specific limitations of the lime concrete as a structural material. The corbelled vault, which is constructed by progressively stepping the courses of stone inward from each side of the room until they meet at the top, is a compression structure that relies on the weight of the stone and the binding capacity of the concrete to maintain its shape, and it does not require the tensile strength that would be needed for a true arch or a true vault. The Maya, who did not develop the true arch, may have been constrained by the specific tensile weakness of their lime concrete, which could not provide the specific binding strength that is needed for the voussoirs of a true arch, and the corbelled vault, which avoids the tensile stresses that a true arch generates, was the specific structural solution that the properties of the Maya concrete permitted. The massive walls of the Maya buildings, which are typically 1 to 2 meters thick and which are constructed from two faces of cut stone with a core of rubble and lime concrete, are another specific response to the specific properties of the Maya concrete. The thick walls, which provide the mass and the stability that the corbelled vault requires, are also a specific response to the relatively low compressive strength of the Maya concrete, which requires a larger cross-section to support a given load than a material with a higher compressive strength would require. The steep pyramid profiles that characterize the Maya ceremonial architecture, with slopes that are typically steeper than the slopes of the Egyptian and the Mesoamerican pyramids of other traditions, may also be related to the specific properties of the Maya concrete, because the steep slopes reduce the volume of fill material that is needed for a given height, and thereby reduce the quantity of concrete that must be produced. The specific optimization of the pyramid profile to minimize the volume of fill material would have been a rational response to the high cost of concrete production, Particularly the high fuel cost and the steep profiles of the Maya pyramids may therefore be a specific expression of the specific economic constraints of the Maya construction tradition. The specific question of the fuel efficiency of the Maya lime kilns has been addressed by researchers who have conducted experimental firings of replica kilns using the same types of wood and the same quantities of limestone that the Maya are believed to have used. The experimental firings have revealed that the fuel efficiency of the Maya open kilns is approximately 1 to 2 tons of wood per ton of quicklime produced, a ratio that is significantly less efficient than the ratio of modern industrial kilns, which can produce 1 ton of quicklime with approximately 200 to 300 kilograms of fuel, but that is consistent with the specific technology that the Maya possessed and with the specific conditions of the open fire calcination process. The specific types of wood that the Maya used for the kiln firings have been identified through the analysis of charcoal fragments that have been recovered from the archaeological remains of the Maya kilns. The analysis has revealed that the Maya used a variety of hardwood species, including the sapodilla, the logwood, the habin, and the zalam, species that are characterized by their high density, their high calorific value, and their ability to produce a sustained even heat that is suitable for the calcination process. The specific selection of the wood species for the kiln firings was not random, but was guided by the specific knowledge of the burning properties of the different species, knowledge that was part of the traditional ecological knowledge of the Maya communities. The specific question of whether the Maya developed any innovations in kiln design that improved the fuel efficiency of the calcination process has been addressed by the archaeological investigation of the kiln remains and by the comparison of the Maya kilns with the kilns of other lime-producing civilizations. The investigation has revealed that the Maya kilns were generally simpler in design than the kilns that were used in the Old World lime industry, lacking the specific features such as the draft channels and the dampers that were used in the European shaft kilns to control the airflow and to improve the fuel efficiency. The simplicity of the Maya kilns may reflect the specific abundance of fuel wood in the tropical forest, which reduced the incentive to develop fuel-efficient kiln designs, or it may reflect the specific limitations of the available construction materials and the available engineering knowledge. The specific question of the environmental sustainability of the Maya lime production, which has been debated by environmental archaeologists and by ecologists, is one that connects the Maya concrete tradition to the broader question of the environmental impact of the Maya civilization and to the specific debate about the role of environmental degradation in the Maya decline. The debate has produced a range of views, from the view that the Maya lime production was a significant driver of the deforestation that contributed to the Maya decline, to the view that the Maya managed their forest resources sustainably, and that the lime production was not a significant factor in the environmental degradation. The resolution of the debate requires the specific estimation of the total wood consumption for lime production over the entire period of the Maya civilization, the comparison of this consumption with the total forest area, and the total forest regeneration rate of the Maya lowlands, and the evaluation of the specific impact of the wood consumption on the specific ecological conditions that are believed to have contributed to the Maya decline. The core problem with Maya concrete is not that it is poorly understood. It is in fact increasingly well understood, thanks to decades of scientific analysis that have revealed its specific chemistry, its specific microstructure, and its specific mechanical properties. The core problem is that the material should not have survived. Lime concrete in its simplest form is a relatively weak, relatively porous, relatively vulnerable material that deteriorates rapidly when it is exposed to the specific conditions of the tropical lowland environment. The high temperatures, the torrential rains, the cycles of wetting and drying, the acidic groundwater, and the biological attack of roots, fungi, and bacteria. A simple lime concrete made from quicklime and crushed limestone without any additional treatment or additives would deteriorate within decades in the tropical environment, crumbling and dissolving under the relentless assault of the water, the heat, and the biology of the jungle. The Maya concrete has not deteriorated within decades. It has survived for more than 1,000 years. In some cases, it has survived for more than 2,000 years. The floors of the plazas, the surfaces of the roads, the linings of the water reservoirs, the plaster of the walls, and the stucco of the facades have endured the tropical environment for centuries, maintaining their structural integrity and their waterproof character despite the specific conditions that should have destroyed them. The survival of the Maya concrete is not a puzzle. It is a contradiction between what the material should do and what it actually does, between the expected performance of simple lime concrete and the observed performance of the specific material that the Maya produced. But here is the problem. The resolution of this contradiction has required the identification of the specific features of the Maya concrete that distinguish it from simple lime concrete and that explain its extraordinary durability. The investigation of these features, which has been conducted using the most advanced analytical techniques of modern materials science, has revealed that the Maya concrete is not a simple lime concrete. It is a complex engineered material that contains specific additives, specific microstructural features, and specific chemical characteristics that enhance its durability and that distinguish it from the lime concretes of other ancient civilizations. The first specific feature that has been identified is the presence of organic additives in the Maya concrete. The analysis of Maya concrete samples using Fourier transform infrared spectroscopy, gas chromatography mass spectrometry, and other analytical techniques has revealed the presence of organic compounds in the concrete that are derived from specific plant sources, including the bark of trees, the sap of cacti, the gum of specific shrubs, and the juice of specific fruits. The specific organic compounds that have been identified include polysaccharides, proteins, lipids, and tannins, and the specific plants from which they are derived include the chukum tree, the holol cactus, the pyxoi bark, and other species that are native to the Maya lowlands and that were known to the Maya for their specific properties. The role of these organic additives in the performance of the Maya concrete has been the subject of extensive research that has revealed specific mechanisms by which the organic compounds improve the properties of the lime concrete. The polysaccharides, which are long-chain sugar molecules that are present in the sap and the gum of the specific plants, act as water retention agents that slow the drying of the concrete and that allow the carbonation process to proceed more completely and more uniformly, producing a harder and a more durable material. The proteins which are present in the sap of certain cacti act as binding agents that improve the adhesion of the lime particles to each other and to the aggregate particles, increasing the cohesive strength of the material. The tannins, which are present in the bark of specific trees, act as fungicides and as bactericides that protect the concrete from the biological attack that is one of the primary causes of deterioration in the tropical environment. And it gets worse for anyone who assumed the Maya were unsophisticated builders. The specific organic additive that has received the most attention from the researchers is the extract of the chukum tree, a species that is native to the Yucatan and that produces a dark, resinous sap that has been used by the indigenous peoples of the region for centuries as a waterproofing agent and as a preservative. The analysis of the chukum extract has revealed that it contains specific polyphenolic compounds that react with the calcium hydroxide in the lime to form calcium polyphenol complexes, a type of chemical bond that is resistant to water dissolution and that significantly improves the waterproofing of the concrete. The chukum-treated lime concrete, which is darker in color than the untreated concrete due to the presence of the polyphenolic compounds, has been shown in laboratory tests to have a water absorption rate that is approximately 1/5 of the rate of untreated lime concrete, a reduction that explains the extraordinary waterproof performance of the Maya concrete in the tropical environment. The second specific feature that has been identified is the microstructural organization of the Maya concrete, which differs from the microstructure of simple lime concrete in ways that enhance its mechanical properties and its durability. The analysis of the Maya concrete microstructure using scanning electron microscopy and transmission electron microscopy has revealed that the calcium carbonate crystals that form during the carbonation process are organized in specific patterns that are different from the random patterns that are found in simple lime concrete. The Maya concrete crystals are smaller, more uniform, and more densely packed than the crystals in simple lime concrete, and the specific crystal structure that they form, which is predominantly calcite rather than the less stable aragonite, is more resistant to dissolution and to mechanical damage. The specific microstructural features of the Maya concrete have been attributed to the combined effects of the organic additives and of the specific production conditions, including the lower calcination temperature, the extended aging of the lime putty, and the specific mixing and application procedures that the Maya used. The organic additives, by controlling the rate of water loss and by providing specific nucleation sites for the formation of calcium carbonate crystals, influence the size, the shape, and the orientation of the crystals, producing a microstructure that is more uniform and more compact than the microstructure that would be produced without the additives. The lower calcination temperature, by producing a more reactive quicklime with a higher surface area, promotes the formation of a finer and more uniform crystal structure during the carbonation process. The third specific feature that has been identified is the presence of pozzolanic reactions in some Maya concrete samples. Pozzolanic reactions, which we discussed in detail in our episode on Roman concrete, are chemical reactions between the calcium hydroxide in the lime and the siliceous and aluminous compounds in the pozzolanic material, producing calcium silicate hydrate and calcium aluminate hydrate gels that are the primary binding phases in hydraulic cement. The identification of pozzolanic reaction products in Maya concrete was unexpected because the Maya lowlands do not contain the volcanic ash that is the most common pozzolanic material in the ancient world, and the source of the pozzolanic material in the Maya concrete was initially a mystery. The mystery was resolved when researchers identified the specific source of the pozzolanic material as the clay minerals that are present in the soils and in the weathered limestone of the Maya lowlands. The clay minerals, which include specific types known as kaolinite and montmorillonite, undergo a chemical transformation when they are heated to temperatures above approximately 500 degrees Celsius, a transformation that converts the crystalline clay minerals into an amorphous, reactive form that can participate in pozzolanic reactions with the calcium hydroxide in the lime. The Maya, by including the local clay minerals in their concrete mix, either deliberately or incidentally, introduced a pozzolanic component that reacted with the lime to produce calcium silicate hydrate gels, the same binding phases that give Roman concrete and modern Portland cement their hydraulic properties and their resistance to water. But here is what makes this truly terrifying. The question of whether the Maya deliberately included the clay minerals in their concrete as a pozzolanic additive, or whether the clay was included incidentally as an impurity in the limestone aggregate, is one that has significant implications for the evaluation of the Maya material's engineering capability. If the inclusion was deliberate, it would mean that the Maya possessed a practical understanding of pozzolanic chemistry that is comparable to the understanding that the Romans possessed, a finding that would significantly elevate the evaluation of the Maya material's engineering tradition. If the inclusion was incidental, it would mean that the Maya benefited from a fortunate accident that improved the properties of their concrete without their understanding the specific mechanism that was responsible for the improvement. The evidence on this question is mixed. The analysis of Maya concrete samples from different sites and different periods has revealed that the concentration of clay minerals in the concrete varies significantly, with some samples containing high concentrations that are consistent with deliberate addition, and other samples containing low concentrations that are consistent with incidental inclusion. The variation in the clay concentration, combined with the variation in the organic additives and in the other features of the concrete, suggests that the Maya concrete tradition was not a single, uniform recipe, but a diverse tradition that varied from site to site, from period to period, and from application to application, with different builders using different formulations to address the specific requirements of each project. The comparison between Maya concrete and Roman concrete, which is one of the most productive areas of research in the study of ancient construction materials, has revealed both similarities and differences that illuminate the specific achievements and the specific limitations of each tradition. Both the Maya and the Romans used lime as the primary binding agent in their concrete, and both traditions incorporated additives that enhanced the performance of the material. The Romans used volcanic ash as a pozzolanic additive that gave their concrete hydraulic properties and the ability to set underwater. The Maya used organic additives that improved the waterproofing and the biological resistance of their concrete, and they may have used clay minerals as a pozzolanic additive that gave their concrete some hydraulic properties. The Roman concrete, which contained a strong pozzolanic component, developed greater compressive strength and greater resistance to water than the Maya concrete. The Maya concrete, which contained the organic additives, developed greater resistance to biological attack and greater waterproofing than the Roman concrete. The specific question of whether the Maya concrete can properly be called concrete at all, or whether it should be classified as a mortar or a plaster, has been debated by scholars who note that the term concrete is typically reserved for materials that contain a coarse aggregate, such as gravel or crushed stone, that is bound by a cementitious matrix. The Maya material, which typically contains crushed limestone as the aggregate and lime as the binding agent, meets the definition of concrete in its composition, but differs from modern concrete in its specific properties, particularly its lower compressive strength and its greater porosity. The terminological debate, while it may seem academic, has practical implications for the evaluation of the Maya material, because the classification of the material as concrete rather than as mortar or plaster implies a specific level of structural capability that the material may or may not possess. The specific role of the nopal cactus mucilage in the Maya concrete deserves detailed examination, because it is one of the most well-studied of the organic additives, and because the specific mechanisms by which it improves the properties of the lime concrete have been documented in considerable detail. The nopal cactus, which is known scientifically as Opuntia ficus indica and which is native to the Americas and widely cultivated in the Maya region, produces a thick, viscous mucilage from its pads that has been used by the indigenous peoples of Mesoamerica for centuries as a food, as a medicine, and as an additive for construction materials. The mucilage of the nopal cactus is a complex mixture of polysaccharides, including galacturonic acid, rhamnose, galactose, arabinose, and xylose, that forms a viscous gel when mixed with water, and that interacts with the calcium hydroxide in the lime to modify the specific properties of the concrete in several important ways. The first effect of the nopal mucilage is the improvement of the workability of the lime concrete, because the viscous gel reduces the friction between the lime particles and the aggregate particles, allowing the concrete to be spread and shaped more easily and more uniformly. The second effect is the improvement of the water retention of the concrete, because the polysaccharides in the mucilage bind water molecules and slow the evaporation of the water from the concrete surface, allowing the carbonation process to proceed more completely and producing a harder and more durable material. The third effect is the modification of the crystal growth during the carbonation process, because the polysaccharide molecules interact with the calcium carbonate crystals as they form, influencing their size, their shape, and their orientation, and producing a microstructure that is more uniform and more compact than the microstructure that is produced without the mucilage. The specific improvements in the properties of the lime concrete that are produced by the addition of the nopal mucilage have been quantified by laboratory tests that have compared the properties of mucilage-treated and untreated lime concrete samples. The tests have shown that the mucilage-treated samples have compressive strengths that are approximately 50 to 100% higher than the untreated samples, water absorption rates that are approximately 30 to 50% lower, and resistance to salt crystallization damage that is approximately 2 to 3 times greater. The specific magnitude of the improvements depends on the specific concentration of the mucilage, the specific curing conditions, and the specific composition of the lime, but the general pattern of improvement is consistent across the studies and confirms the specific role of the nopal mucilage in enhancing the properties of the Maya concrete. The modern applications of the nopal mucilage as an additive for lime concrete have been explored by conservation scientists who are working to develop sustainable restoration materials for the conservation of historic buildings and monuments. The specific advantage of the nopal mucilage as a conservation material is that it is chemically compatible with the original lime concrete, that it is produced from a renewable and widely available natural resource, and that it is non-toxic and environmentally benign. The use of the nopal mucilage in the conservation of historic lime concrete buildings has been tested at several sites in Mexico and in other countries, and the results have demonstrated that the mucilage-treated lime concrete provides a durable and a compatible repair material that is superior in several respects to the synthetic polymers and the Portland cement-based materials that are commonly used in conservation practice. The question of what other organic additives the Maya may have used, beyond the chucum extract and the nopal mucilage that have been the focus of the most intensive research, is one that is being explored through the analysis of additional concrete samples from different sites and different periods. The analysis has identified traces of a variety of organic compounds that may be derived from additional plant sources, including the sap of the sapodilla tree, the gum of the copal tree, the juice of the agave plant, and the extract of various bark species, and the specific role of each of these additives in the performance of the concrete is being investigated through experimental replications that test the effect of each additive on the specific properties of the lime concrete. The specific comparison between the Maya concrete and modern Portland cement concrete in terms of their environmental impact is one of the most productive areas of current research because the comparison reveals specific advantages of the Maya approach that are directly relevant to the urgent challenge of reducing the carbon emissions of the modern construction industry. The production of Portland cement, which is the primary binding agent of modern concrete, requires the heating of a mixture of limestone and clay to a temperature of approximately 1450 degrees Celsius in a rotary kiln, a process that releases approximately 800 kilograms of carbon dioxide for every ton of cement that is produced. The production of the quicklime that is the basis of the Maya concrete requires the heating of limestone to approximately 750 to 850 degrees Celsius, a process that releases approximately 600 kilograms of carbon dioxide for every ton of quicklime that is produced, but that reabsorbs approximately 440 kilograms of carbon dioxide during the carbonation process, producing a net emission of approximately 160 kilograms of carbon dioxide per ton of binding agent, approximately 1/5 of the net emission of the Portland cement production. The specific carbon accounting of the Maya concrete versus the Portland cement concrete is complicated by the differences in the binding capacity of the two materials, and by the differences in the specific amounts of binding agent that are needed for the different applications. The Portland cement, which produces stronger concrete that can be used in thinner sections, requires less binding agent per unit of structural capacity than the Maya lime concrete, which produces weaker concrete that must be used in thicker sections to achieve the same structural capacity. The comparative carbon analysis, which takes into account the specific binding capacity and the specific structural requirements of each material, shows that the Maya concrete approach produces approximately 30 to 50% less carbon dioxide per unit of structural capacity than the Portland cement approach, a reduction that is significant and that could contribute to the reduction of the construction industry's carbon footprint. The specific question of whether the Maya concrete approach can be adapted to the structural requirements of modern construction, which include the specific demands of multi-story buildings, of bridges, of dams, and of other structures that require the specific compressive and tensile strength that modern Portland cement concrete provides, is one that is being addressed by modern materials scientists who are working to develop lime-based concretes that combine the environmental advantages of the Maya approach with the structural capabilities of the Portland cement approach. The specific research directions include the development of lime pozzolan concretes that combine the lime binder with modern pozzolanic materials, such as fly ash and ground granulated blast furnace slag, to produce a material with improved structural properties. The development of bio-additive lime concretes that incorporate the specific organic additives of the Maya tradition into modern lime formulations to improve the durability and the waterproofing of the material, and the development of hybrid lime cement concretes that combine a small amount of Portland cement with a large amount of lime to produce a material that has better environmental performance than the Portland cement concrete and better structural performance than the pure lime concrete. The specific investigation of the pozzolanic activity of the clay minerals in the Maya concrete has been one of the most active areas of research in the Maya concrete field, because the identification and the quantification of the pozzolanic reaction products provides specific evidence for the degree of hydraulic behavior in the Maya concrete and for the specific mechanisms by which the material achieves its durability. The pozzolanic reaction products that have been identified in the Maya concrete through X-ray diffraction analysis and through transmission electron microscopy include calcium silicate hydrate gel, which is the primary binding phase in modern Portland cement and which provides the specific compressive strength and the specific water resistance that are the distinctive properties of hydraulic cement, and calcium aluminate hydrate, which is a secondary binding phase that provides additional strength and additional resistance to chemical attack. The specific concentration of the pozzolanic reaction products varies from sample to sample, with some samples showing relatively high concentrations that indicate a significant degree of pozzolanic activity, and other samples showing low concentrations that indicate a minimal degree of pozzolanic activity. The variation in the pozzolanic activity has been correlated with the variation in the clay mineral content of the concrete, with the samples that contain higher concentrations of clay minerals showing higher concentrations of pozzolanic reaction products. The correlation supports the hypothesis that the clay minerals are the specific source of the pozzolanic activity in the Maya concrete, and that the degree of pozzolanic activity is determined by the specific concentration of the clay minerals that are included in the mix. The question of whether the thermal activation of the clay minerals, which converts the crystalline clay minerals into the amorphous, reactive form that can participate in pozzolanic reactions, occurred during the calcination of the limestone, or as a separate process, is one that has been addressed by researchers who have analysed the specific temperatures at which the clay minerals undergo the dehydroxylation reaction that produces the amorphous form. The analysis has shown that the dehydroxylation of kaolinite, the most common clay mineral in the Maya lowlands, occurs at approximately 500 to 600 degrees Celsius, a temperature that is below the calcination temperature of the limestone, and that would have been reached in the lower zones of the lime kiln during the calcination process. The implication is that the thermal activation of the clay minerals could have occurred as an incidental consequence of the calcination process without any deliberate action by the Maya kiln operators, and that the pozzolanic activity of the Maya concrete may have been an unintended benefit of the lime production process rather than a deliberate result of the Maya materials engineering. The question remains open, however, because some Maya concrete samples contain concentrations of clay minerals that are higher than would be expected from incidental inclusion, suggesting that the Maya may have deliberately added clay to their concrete in some cases, even if they did not understand the specific chemical mechanism by which the clay improved the properties of the material. The deliberate addition of clay guided by the empirical observation that the clay-containing concrete performed better than the clay-free concrete, would be consistent with the general pattern of empirical innovation that characterizes the Maya materials engineering tradition, and would be another example of the specific way in which the Maya developed their materials through practical observation rather than through theoretical analysis. The specific question of how the presence of the pozzolanic reaction products affects the long-term durability of the Maya concrete has been addressed by accelerated aging tests, in which Maya concrete samples were subjected to simulated environmental conditions, including cycles of wetting and drying, exposure to acidic solutions, and exposure to elevated temperatures, and the rate of deterioration was measured as a function of the pozzolanic reaction product content. The tests showed that the samples with higher pozzolanic reaction product content deteriorated more slowly than the samples with lower content, confirming the specific role of the pozzolanic reactions in enhancing the durability of the Maya concrete. The broader significance of the identification of pozzolanic reactions in the Maya concrete is that it establishes a specific connection between the Maya concrete tradition and the Roman concrete tradition, two traditions that were developed independently on opposite sides of the Atlantic Ocean, and that both exploited the specific chemistry of the pozzolanic reaction to produce durable, hydraulic construction materials. The independent development of pozzolanic concrete by two unrelated civilizations demonstrates that the exploitation of the pozzolanic reaction is a convergent technological development, a specific solution to the specific problem of producing durable construction materials that was discovered independently by different civilizations, working with different materials in different environments. The specific investigation of the self-healing properties of the Maya concrete has been one of the most exciting recent developments in the Maya concrete research, because the identification of self-healing mechanisms in the Maya material connects the ancient tradition to one of the most active areas of modern materials science research. The self-healing of lime concrete is a natural process in which the calcium hydroxide that remains in the interior of the concrete, unreacted from the original slaking process, dissolves in the water that penetrates through cracks in the concrete surface and is transported to the crack, where it reacts with the carbon dioxide in the atmosphere to form calcium carbonate that fills the crack and restores the integrity of the surface. The self-healing process has been documented in Maya concrete through the microscopic examination of healed cracks in concrete samples from archaeological sites. The examination has revealed that the cracks in the Maya concrete are filled with secondary calcium carbonate crystals that were deposited by the self-healing process, and that the secondary crystals have a specific morphology and a specific chemistry that distinguish them from the primary calcium carbonate crystals of the original concrete. The secondary crystals are typically larger and more blocky than the primary crystals, and they form a dense, cohesive fill that effectively seals the crack and prevents the further penetration of water. The specific role of the organic additives in promoting the self-healing process has been investigated by comparing the self-healing rate of Maya concrete samples with and without the organic additives. The investigation has shown that the additive-treated samples will heal more quickly and more completely than the untreated samples, a finding that is attributed to the specific effect of the polysaccharides in the organic additives on the nucleation and the growth of the secondary calcium carbonate crystals. The polysaccharides, which act as nucleation sites for the crystal growth and which control the rate of water flow through the crack, promote the formation of a dense, well-bonded crack fill that is more effective at sealing the crack than the fill that is produced in the absence of the additives. The comparison between the self-healing properties of the Maya concrete and the self-healing properties of the Roman concrete reveals specific similarities and specific differences that reflect the specific chemistries of the two materials. Both materials exhibit self-healing behavior that is driven by the dissolution and the reprecipitation of calcium-bearing phases, but the specific phases that are involved are different. the Roman concrete heals through the dissolution and reprecipitation of the calcium silicate hydrate and the calcium aluminate hydrate phases that are produced by the pozzolanic reaction, while the Maya concrete heals primarily through the dissolution and reprecipitation of the calcium hydroxide that remains in the concrete from the original lime production. The specific healing mechanisms are different, but the result is the same. A material that has the ability to repair minor damage to itself without external intervention, a property that contributes to the extraordinary durability of both materials. The modern materials science community has been particularly interested in the self-healing properties of the ancient concretes because the development of self-healing construction materials is one of the most active areas of modern materials research, driven by the specific need to reduce the maintenance costs and to extend the service life of the modern infrastructure. The ancient concretes, both Roman and Maya, provide specific models for the design of self-healing materials, and the specific mechanisms that produce the self-healing behavior in the ancient materials are being studied and adapted for the development of modern self-healing concretes that combine the specific self-healing properties of the ancient materials with the specific structural properties of the modern Portland cement concrete. The specific question of how the Maya concrete performed under the seismic conditions of the Maya lowlands, which are located in a region of moderate seismic activity, has been addressed by structural engineers who have analyzed the specific response of the Maya structures to the seismic forces that they would have experienced over their lifetime. The analysis has revealed that the Maya structures, which are predominantly massive compression structures with thick walls and heavy platforms, are relatively resistant to seismic forces because the mass and the compressive loading of the structures provide the inertial stability that resists the horizontal forces of the earthquake. The lime concrete that binds the rubble cores of the structures provides the specific cohesion that prevents the rubble from collapsing under the seismic shaking, and the specific properties of the Maya concrete, including its moderate compressive strength and its moderate flexibility, allow the concrete to absorb the seismic energy without catastrophic failure. The specific question of how the Maya concrete compares with modern seismic-resistant construction materials in its ability to absorb and dissipate seismic energy has been addressed through the testing of Maya concrete samples under simulated seismic loading conditions. The tests have shown that the Maya concrete, while it is weaker than modern reinforced concrete in its ability to resist the specific tensile and shear forces that earthquakes generate, possesses a specific energy absorption capacity that is comparable to the energy absorption capacity of modern unreinforced masonry, a finding that is consistent with the observed survival of the Maya structures through centuries of seismic activity. The specific evidence of earthquake damage in the Maya structures, which includes specific patterns of cracking, of displacement, and of collapse that are characteristic of seismic damage, has been identified at several Maya sites and has been used to reconstruct the specific seismic history of the Maya region. The analysis of the earthquake damage has revealed that the Maya structures sustained specific damage during specific seismic events, and that the Maya builders repaired the damage using the same lime concrete that was used in the original construction, a practice that demonstrates the specific repairability of the Maya concrete and the specific ability of the Maya builders to maintain their structures through the specific environmental and geological challenges that the lowland environment presented. The broader analysis of the durability of the Maya concrete under the full range of environmental and geological conditions that the Maya lowlands present, including the tropical climate, the heavy rainfall, the biological attack, and the seismic activity, confirms that the Maya concrete was specifically engineered through the empirical process that we have described to resist the specific combination of conditions that the lowland environment imposes. The specific formulation of the Maya concrete, with its organic additives, its compact microstructure, its pozzolanic reaction products, and its self-healing capability, addresses each of the specific degradation mechanisms that the lowland environment activates, producing a material that is specifically adapted to the specific challenges of the specific environment in which it was developed and used. The specific investigation of the durability of the Maya concrete under the specific conditions of the cenote environment, the natural sinkholes that are formed by the dissolution of the limestone bedrock and that provide access to the underground water table, has provided additional evidence for the waterproofing and the chemical resistance of the Maya material. The Maya used their lime concrete to construct structures on the edges and the walls of the cenotes, including stairways, platforms and retaining walls that have been exposed to the specific chemical conditions of the cenote water, including the high mineral content, the specific acidity, and the biological activity that characterize the cenote environment. The survival of these structures, which have been exposed to the cenote conditions for more than 1,000 years, provides direct evidence for the chemical durability of the Maya concrete and for the specific resistance of the material to the dissolution and the biological attack that the cenote environment presents. The investigation of the microbiological communities that colonize the surface of the Maya concrete in the tropical environment has revealed a complex ecosystem of bacteria, fungi, algae, and lichens that interact with the concrete in specific ways that can be either destructive or protective. The destructive interactions include the production of organic acids by the bacteria and the fungi that dissolve the calcium carbonate of the concrete surface, and the mechanical penetration of the fungal hyphae and the lichen thalli into the pore structure of the concrete. The protective interactions include the production of biofilms by the bacteria and the algae that cover the concrete surface and that reduce the penetration of the rainwater and the atmospheric pollutants, and the production of calcified structures by specific species of cyanobacteria and algae that deposit calcium carbonate on the concrete surface and that effectively repair the minor damage that the dissolution process produces. The balance between the destructive and the protective microbial interactions determines the specific rate of biodeterioration of the Maya concrete, and the specific formulation of the Maya concrete, which includes the tannins and the other phenolic compounds that act as natural antimicrobial agents, shifts the balance toward the protective interactions by selectively inhibiting the growth of the destructive species while allowing the growth of the protective species. The selective antimicrobial action of the Maya organic additives is one of the most sophisticated aspects of the Maya concrete engineering because it demonstrates a specific understanding of the interaction between the construction material and the biological environment that is comparable to the understanding that characterizes the modern field of biodeterioration science. The specific investigation of the long-term carbonation of the Maya concrete, the process by which the calcium hydroxide in the interior of the concrete gradually converts to calcium carbonate through the reaction with atmospheric carbon dioxide, has revealed that the carbonation process in the Maya concrete is more complete and more uniform than the carbonation in simple lime concrete, producing a material with a higher proportion of the stable calcite phase and a lower proportion of the less stable amorphous and vaterite phases. The more complete carbonation, which is attributed to the specific effect of the organic additives on the water retention and the crystal growth during the carbonation process, produces a material that is more chemically stable and more resistant to dissolution than the simple lime concrete, contributing to the extraordinary durability that characterizes the Maya concrete in the tropical environment. The specific analysis of the Maya concrete from the site of Caracol in Belize has provided additional evidence for the diversity and the sophistication of the Maya concrete tradition. The Caracol concrete, which has been analyzed by researchers at the University of Central Florida, shows a distinctive formulation that includes a higher proportion of calcite aggregate and a lower proportion of organic additives than the concrete from the Yucatan sites, reflecting the specific geological and botanical conditions of the Belizean lowlands. The Caracol analysis has also revealed specific evidence of the deliberate layering of the concrete, with different layers containing different proportions of additives and different aggregate sizes, suggesting a specific construction strategy in which the different layers serve different functions, with the inner layers providing structural support and the outer layers providing waterproofing and surface finish. The deliberate layering of the concrete, which has been confirmed at several other Maya sites, demonstrates a specific level of construction planning and materials management that is comparable to the layered construction systems that are used in modern construction practice. The specific number of layers varies from site to site and from application to application, with the reservoir linings typically containing the most layers and the structural fills containing the fewest, a pattern that reflects the specific waterproofing requirements of each application. The cumulative evidence from the chemical analysis, the microstructural examination, the mechanical testing, and the experimental replication converges on a specific conclusion. The Maya concrete was a deliberately engineered material whose specific properties were the result of specific formulation choices that were guided by centuries of empirical observation and intergenerational knowledge transmission. The specific organic additives, the specific production conditions, and the specific application techniques that the Maya used were not random. They were the products of a systematic, empirical process of materials development that produced a material of extraordinary sophistication and extraordinary durability, a material that challenges the modern assumption that advanced materials engineering requires the formal scientific knowledge that the modern world considers essential. The investigation of Maya concrete has been conducted by archaeologists, materials scientists, chemists, geologists, and conservation specialists over a period of several decades, and it has produced a body of research that has transformed the understanding of the Maya construction tradition, and that has revealed a level of materials engineering sophistication that was not anticipated by the earlier generations of Maya scholars. The investigation has proceeded along several major tracks, each of which has contributed specific insights to the overall understanding of the material. The first major track of investigation has been the chemical and mineralogical analysis of Maya concrete samples from archaeological sites across the Maya lowlands, aimed at determining the specific composition, the specific microstructure, and the specific properties of the material. The analysis has been conducted using a battery of modern analytical techniques, including X-ray diffraction, which identifies the specific mineral phases that are present in the sample, scanning electron microscopy, which reveals the microstructure of the material at magnifications of up to 50,000 times, energy dispersive X-ray spectroscopy, which determines the elemental composition of specific features within the microstructure, Fourier transform infrared spectroscopy, which identifies the specific organic and inorganic compounds that are present, and mechanical testing, which measures the compressive strength, the tensile strength, and the flexural strength of the material. The results of the analytical program have been both revealing and surprising. The analyses have confirmed that the basic binding agent of the Maya concrete is calcium carbonate, the product of the carbonation of the calcium hydroxide that is produced by the slaking of quicklime, a finding that is consistent with the expected chemistry of lime concrete. But the analyses have also revealed the specific features that we have described, the organic additives, the specific microstructural organization, and the pozzolanic reaction products that distinguish the Maya concrete from simple lime concrete and that explain its extraordinary durability. The second major track of investigation has been the experimental replication of Maya concrete, aimed at testing the proposed formulations by producing concrete samples using the specific materials and the specific procedures that the Maya are believed to have used, and then testing the samples for their specific properties. The experimental replications have been conducted by materials scientists who have worked in collaboration with archaeologists and with indigenous Maya craftsmen who maintain the traditional knowledge of lime production that has been transmitted through their communities. The collaboration with the indigenous Maya craftsmen has been one of the most valuable aspects of the experimental replication program because the craftsmen possess specific knowledge about the production and the use of lime concrete that is not available from any written source. and that has been transmitted through oral tradition and through practical demonstration over many generations. The specific knowledge that the craftsmen have contributed includes the identification of the specific tree species whose bark and sap are used as organic additives, the specific procedures for the collection and the preparation of the additives, the specific proportions in which the additives are mixed with the lime, and the specific techniques for the application and the curing of the concrete. The experimental replications have confirmed that the specific organic additives that the Maya used, particularly the extract of the chucum tree and the mucilage of the nopal cactus, significantly improve the properties of the lime concrete. Concrete samples that were prepared with the organic additives showed higher compressive strength, lower water absorption, greater resistance to biological attack, and greater durability under the simulated tropical conditions than the samples that were prepared without the additives. The magnitude of the improvement was significant, with the additive-treated samples showing compressive strengths that were approximately 2 to 3 times higher than the untreated samples, and water absorption rates that were approximately 1/3 to 1/5 of the untreated samples. The numbers are striking when we compare the specific properties of the Maya concrete with the properties of other ancient and modern construction materials. The compressive strength of the Maya concrete, which ranges from approximately 3 to 10 megapascals, depending on the specific formulation and the specific curing conditions, is lower than the compressive strength of Roman concrete, which ranges from approximately 5 to 20 megapascals and is much lower than the compressive strength of modern Portland cement concrete, which ranges from approximately 20 to 50 megapascals. However, the compressive strength of the Maya concrete is significantly higher than the compressive strength of simple lime concrete without additives, which is typically less than 2 megapascals, demonstrating that the specific Maya formulations produced a material that was substantially stronger than the basic lime concrete from which it was derived. The third major track of investigation has been the study of the specific applications of Maya concrete in the built environment, aimed at understanding the specific functions that the concrete served in the Maya cities, and the specific requirements that each application imposed on the formulation and the properties of the material. The study of the applications has revealed that the Maya used their concrete for an extraordinarily wide range of purposes, including structural fill, wall plaster, floor paving, roof surfacing, water reservoir lining, road surfacing, and sculptural stucco, and that the specific formulation of the concrete was varied to suit the specific requirements of each application. The structural fill applications, in which the concrete was used to bind together the rubble cores of the pyramids, the platforms, and the other large structures, required a concrete that was strong enough to support the weight of the structure and durable enough to maintain its cohesion over centuries of loading and environmental exposure. The floor paving applications, in which the concrete was used to create the smooth, waterproof surfaces of the plazas and the courtyards, required a concrete that was resistant to abrasion, to water penetration, and to the thermal expansion and contraction that the tropical climate imposed. The water reservoir applications, in which the concrete was used to line the reservoirs that stored the rainwater that sustained the Maya cities through the dry season, required a concrete that was completely waterproof and that was resistant to the dissolution and the biological growth that the standing water would promote. The specific evidence that the Maya varied their concrete formulations to suit the specific requirements of each application comes from the analysis of concrete samples from different applications at the same site, which has revealed systematic differences in the composition and the properties of the concrete, depending on the specific function that it served. The floor concretes, for example, typically contain higher concentrations of organic additives than the structural fill concretes, reflecting the greater need for waterproofing and for abrasion resistance in the floor applications. The reservoir linings typically contain the highest concentrations of organic additives and the most compact microstructures of any Maya concrete. reflecting the extreme waterproofing requirements of the reservoir application. The fourth major track of investigation has been the study of the Maya water management systems, which are among the most sophisticated engineering achievements of the Maya civilization, and which relied critically on the waterproofing properties of the Maya concrete for their function. The Maya cities of the lowlands, which are located in a region with a 6-month dry season and with no surface rivers or permanent lakes, depended for their water supply on the collection and the storage of rainwater in large, plastered reservoirs that were designed to hold the water that fell during the rainy season and to release it gradually during the dry season. The design and the construction of the Maya water reservoirs was a major engineering undertaking that required the excavation of large basins, the lining of the basins with waterproof concrete, and the construction of channels and of settling tanks that collected the rainwater from the roofs and the plazas of the city and directed it into the reservoirs. The waterproofing of the reservoir linings was critical for the function of the system because any leakage through the lining would allow the stored water to seep into the porous limestone bedrock and would defeat the purpose of the reservoir. The Maya achieved the necessary waterproofing through the specific formulation of their reservoir concrete, which incorporated the highest concentrations of organic additives, and which was applied in multiple layers to ensure complete coverage and complete sealing. The fifth major track of investigation has been the study of the Maya stucco tradition, the decorative use of lime concrete for the production of sculptural relief, of painted surfaces, and of other decorative elements that adorned the facades and the interiors of the Maya buildings. The Maya stucco tradition, which produced some of the most spectacular examples of architectural decoration in the ancient world, including the monumental stucco masks of the pre-classic period and the detailed narrative reliefs of the classic period, required a specific type of lime concrete that combined the structural properties of a building material with the workability and the aesthetic properties of a sculptural medium. The specific formulation of the Maya stucco, which has been analysed through the examination of surviving stucco fragments and through the experimental replication of the stucco-making process, was different from the formulation of the structural and the paving concretes in several important respects. The stucco was typically made with a finer aggregate, often consisting of crushed shell or finely ground limestone, rather than the coarser crushed limestone that was used in the structural applications. The stucco also contained higher proportions of organic additives, particularly the mucilage of the nopal cactus, which improved the workability of the material and allowed the sculptors to model the complex forms and the fine details that characterize the Maya stucco art. The specific skill of the Maya stucco sculptors, who worked with a material that hardened as it dried and that allowed only a limited time for the modeling and the finishing of the surface, was one of the most demanding and the most specialized skills in the Maya artistic tradition. The sculptors had to work quickly, applying the stucco to the prepared surface and modeling the forms before the material became too stiff to manipulate, a process that required the specific coordination of the mixing, the application, and the modeling operations, and that depended on the specific knowledge of the material's setting behavior under the specific temperature and humidity conditions of the day. The sixth major track of investigation has been the study of the Maya concrete in the context of the broader Mesoamerican construction tradition, aimed at placing the Maya material in the context of the construction practices of the other civilizations of ancient Mexico and Central America, including the Olmec, the Zapotec, the Teotihuacanos, and the Aztec. The comparative study has revealed that the use of lime concrete was widespread in Mesoamerica, and that the Maya tradition, while it was the most extensive and the most sophisticated, was not the only Mesoamerican tradition of lime-based construction. The Teotihuacan tradition, which flourished in central Mexico from approximately the 1st century through the 7th century of the Common Era, used a lime concrete that was similar in its basic chemistry to the Maya concrete, but that differed in its specific formulation and in its specific applications. The Teotihuacan concrete which was used for the construction of the massive pyramids and the residential complexes of the city of Teotihuacan, contained volcanic ash as an aggregate and as a pozzolanic additive, a feature that is absent from the Maya concrete, and that reflects the specific geological conditions of the central Mexican highlands, where volcanic deposits are abundant and where the volcanic ash provides a natural pozzolanic material that is comparable to the volcanic ash that the Romans used in their concrete. The comparison between the Maya concrete and the Teotihuacan concrete illustrates the specific way in which the local geology of each region influenced the specific formulation and the specific properties of the construction materials that were produced. The Maya, working in a limestone environment without volcanic deposits, developed a concrete that relied on organic additives and on the specific properties of the local clay minerals for its enhanced performance. The Teotihuacanos, working in a volcanic environment with abundant volcanic deposits, developed a concrete that relied on the pozzolanic properties of the volcanic ash for its enhanced performance. Each tradition exploited the specific resources that were available in its local environment, producing materials that were adapted to the specific conditions and the specific requirements of each region. The seventh major track of investigation has been the exploration of the potential applications of the Maya concrete technology in the modern construction industry, aimed at determining whether the specific materials and the specific techniques that the Maya developed can be used to produce modern construction materials that are more sustainable, more durable, and more environmentally friendly than the Portland cement concrete that dominates the modern construction industry. The investigation of the modern applications of the Maya concrete technology has been driven by the growing recognition that the production of Portland cement, which is the primary binding agent of modern concrete, is one of the largest industrial sources of carbon dioxide emissions, responsible for approximately 7 to 8% of the total global carbon dioxide emissions, and that the development of alternative binding agents that produce less carbon dioxide is one of the most urgent challenges facing the modern construction industry. The eighth major track of investigation has been the study of the specific Maya road system, known as the Sacbi or Sacbiob in the Maya language, which is one of the most impressive engineering achievements of the Maya civilization, and which relied critically on the waterproofing and the durability of the Maya concrete for its construction and its maintenance. The Sacbiob were elevated, paved roads that connected the major Maya cities and that served as routes of trade, for pilgrimage, for military movement, and for political communication across the Maya lowlands. The construction of the Sacbiob involved the building of a raised causeway of rubble and earth, the compaction of the causeway surface, and the application of a thick layer of lime concrete that provided a smooth, waterproof, all-weather surface that could be used during both the wet season and the dry season. The lime concrete surface of the Sacbiob was typically between 10 and 30 centimeters thick, and it was applied in multiple layers to ensure complete coverage and to provide the specific thickness that was needed for the durability of the surface. The specific formulation of the Sacbi concrete, which was designed to resist the abrasion of foot traffic, the impact of the rain, and the penetration of the roots of the vegetation that grew alongside the road, was one of the most demanding applications of the Maya concrete technology. The most famous of the Sacbiob is the Great Sacbi that connects the cities of Cobar and Yaxchinar in the northern Yucatan, a road that extends for approximately 100 kilometers through the tropical forest, and that was built using an estimated 150,000 cubic meters of fill material, topped with a continuous surface of lime concrete. The construction of this single road required the production of tens of thousands of cubic meters of lime concrete and the consumption of hundreds of thousands of cubic meters of fuel wood, a commitment of resources that is comparable to the resources that were required for the construction of a major pyramid, and that demonstrates the specific importance that the Maya placed on the transportation infrastructure of their civilization. The ninth major track of investigation has been the analysis of the specific degradation mechanisms that have affected the Maya concrete over the centuries, aimed at understanding the specific processes by which the material has deteriorated and at identifying the specific features of the material that have resisted the deterioration. The analysis of the degradation mechanisms has been conducted through the examination of deteriorated concrete samples using scanning electron microscopy, X-ray diffraction, and other analytical techniques, and the results have provided information about the specific chemical, physical, and biological processes that have contributed to the deterioration. The specific degradation mechanisms that have been identified include the dissolution of the calcium carbonate by the acidic rainwater, which removes material from the surface of the concrete and which creates porosity that allows further penetration of the water. The crystallization of salts within the pore structure of the concrete, which generates mechanical stress that cracks and spalls the material. The penetration of tree roots, which exert enormous mechanical forces on the concrete and which introduce organic acids that dissolve the calcium carbonate. The growth of fungi and bacteria, which produce organic acids and enzymes that attack the calcium carbonate and the organic additives. And the thermal expansion and contraction of the concrete, which generates cyclic stresses that fatigue the material and that produce cracking over time. The specific features of the Maya concrete that have resisted these degradation mechanisms include the waterproofing provided by the organic additives, which reduces the penetration of the rainwater and the dissolved salts, the compact microstructure, which reduces the porosity of the material and which limits the space available for the crystallization of salts and for the growth of biological organisms, the pozzolanic reaction products, where present, which provide additional binding capacity and additional resistance to dissolution, and the fungicidal and the bactericidal properties of the tannins and the other phenolic compounds in the organic additives which inhibit the growth of the biological organisms that contribute to the deterioration. The specific balance between the degradation mechanisms and the resistance mechanisms determines the rate of deterioration of the Maya concrete in the tropical environment, and the extraordinary durability of the material is the result of the specific balance that the Maya achieved through their specific formulation, a balance in which the resistance mechanisms are strong enough to counteract the degradation mechanisms for a period of more than 1,000 years. The achievement of this balance was not the result of theoretical calculation. It was the result of centuries of empirical experimentation, of trial and error, of the specific observation of what worked and what did not, and of the specific transmission of the successful formulations from one generation to the next. The 10th major track of investigation has been the study of the specific colors that the Maya applied to their concrete surfaces, including the specific pigments, the specific binding media, and the specific application techniques that were used to produce the polychrome decorations that adorned the facades of the Maya temples and palaces. The Maya painted their buildings in brilliant colors, including red, blue, yellow, green, orange, black, and white, using pigments that were derived from specific mineral and organic sources, and that were applied to the lime concrete surface, using specific binding media and specific techniques that ensured durability and the color stability of the decoration. The most famous of the Maya pigments is Maya blue, a brilliant turquoise blue pigment that is one of the most stable and most durable pigments in the history of art, and that has resisted the fading and the deterioration that have destroyed other ancient pigments over the centuries. Maya blue is produced by the combination of the organic dye indigo, which is derived from the anil plant, with the clay mineral palygorskite, a naturally occurring mineral that is found in specific deposits in the Yucatan Peninsula. The combination of the indigo with the palygorskite produces a hybrid organic-inorganic pigment, in which the indigo molecules are enclosed within the tubular channels of the palygorskite crystal structure, protecting the indigo from the chemical degradation that normally destroys organic dyes and producing a pigment that is resistant to acid, to alkali, to light, and to biological attack. The production of Maya blue, which involves the heating of a mixture of indigo and palygorskite to a specific temperature, approximately 150 to 200 degrees Celsius, is another example of the specific materials engineering capability that the Maya possessed. The specific temperature at which the mixture is heated determines the specific degree to which the indigo is incorporated into the palygorskite structure and the specific color of the resulting pigment, from pale blue at lower temperatures to deep blue at higher temperatures, is controlled by the specific heating conditions. The Maya blue pigment has been the subject of extensive research by modern chemists and materials scientists, and the specific mechanism by which the indigo is incorporated into the palygorskite has been determined through X-ray diffraction, nuclear magnetic resonance spectroscopy, and molecular modeling studies. The specific relationship between the Maya blue pigment and the Maya concrete is that the pigment was applied to the lime concrete surface as a paint, using a binding medium that was probably derived from lime water or from one of the organic additives that were used in the concrete production. The application of the pigment to the fresh or the recently applied lime concrete allowed the pigment to be incorporated into the surface layer of the concrete as the carbonation process proceeded, producing a painted surface that was integral to the concrete, rather than merely applied to its surface, and that was therefore more durable and more resistant to weathering than a paint that was applied to a dry, fully carbonated surface. The 11th major track of investigation has been the study of the specific conservation methods that are being developed for the preservation of the Maya concrete at the archaeological sites. Methods that must balance the need to protect the concrete from further deterioration with the need to preserve the specific character and the specific historical information that the concrete contains. The conservation of Maya concrete is one of the most challenging tasks in the field of archaeological conservation because the material is exposed to the specific tropical conditions that promote deterioration, and because the material contains the specific organic additives and the specific microstructural features that are essential for the understanding of the Maya construction tradition, and that must be preserved intact. The specific conservation methods that have been developed for the Maya concrete include the consolidation of deteriorated surfaces using lime water, which deposits calcium carbonate in the pores of the concrete and strengthens the material, the application of protective coatings that reduce the penetration of water and the exposure to the sun, the control of the vegetation growth that causes mechanical damage to the concrete, and the management of the drainage to prevent the accumulation of water on and around the concrete surfaces. The development of these conservation methods has been guided by the principle that the conservation materials and the conservation methods should be compatible with the original material and should not introduce substances or conditions that could cause further deterioration. The 12th major track of investigation has been specific analysis of the mechanical properties of Maya concrete in comparison with other ancient and modern construction materials, aimed at placing the Maya material in the broader context of construction materials engineering and at evaluating its specific strengths and limitations relative to other materials. The mechanical testing of Maya concrete samples, which has been conducted using standard materials testing procedures, including compression testing, flexural testing, and tensile testing, has produced a comprehensive database of the mechanical properties of the material that can be compared with the properties of other construction materials. The compressive strength of the Maya concrete, which is the property that is most critical for its structural applications, ranges from approximately 3 to 10 megapascals, depending on the specific formulation, the specific curing conditions, and the specific age of the sample. The compressive strength of the Maya concrete is lower than the compressive strength of Roman pozzolanic concrete, which ranges from approximately 5 to 20 megapascals, and much lower than the compressive strength of modern Portland cement concrete, which ranges from approximately 20 to 50 megapascals for standard grades. However, the compressive strength of the Maya concrete is higher than the compressive strength of simple lime concrete without additives, which is typically less than 2 megapascals, and it is sufficient for the specific structural applications for which the Maya used the material, including the construction of pyramids, platforms, and walls which are predominantly compressive structures that do not require the specific tensile and flexural strengths that modern reinforced concrete provides. The flexural strength of the Maya concrete, which is the property that is most critical for its paving and surfacing applications, has been measured at approximately 1 to 3 megapascals, a value that is sufficient for the specific paving applications in which the material is subjected to the bending forces of foot traffic and of thermal expansion. The tensile strength of the Maya concrete, which is the weakest mechanical property of the material, has been measured at approximately 0.3 to 1 megapascal, a value that is comparable to the tensile strength of other lime-based materials, and that reflects the specific limitation of lime concrete as a material that is strong in compression but weak in tension. The specific durability properties of the Maya concrete, including its resistance to water penetration, its resistance to salt crystallization, its resistance to freeze-thaw cycling, and its resistance to biological attack, have been measured using standard durability testing procedures and have been found to be superior to the durability properties of simple lime concrete without additives. The specific superiority of the Maya concrete in the durability tests is attributed to the specific organic additives and the specific microstructural features that we have described, and the magnitude of the superiority, which ranges from approximately 2 to 5 times greater durability, depending on the specific test, confirms the specific role of the Maya formulations in enhancing the long-term performance of the material. The 13th major track has been the study of the Maya concrete in the specific context of heritage conservation. The conservation of the Maya archaeological sites, which are exposed to the destructive conditions of the tropical environment, and which require continuous maintenance to prevent the deterioration of the ancient structures, has become one of the most important and most challenging tasks in the field of heritage conservation. The specific challenge of the Maya site conservation is that the conservation materials and the conservation methods must be compatible with the original Maya concrete, which has specific chemical and physical properties that are different from the properties of the modern conservation materials, and that the introduction of incompatible materials can cause accelerated deterioration rather than preservation. The specific conservation approach that has been developed for the Maya sites is based on the principle of like with like, in which the conservation materials are formulated to be as similar as possible to the original Maya concrete, using the same basic materials, lime and crushed limestone, and the same organic additives, nopal mucilage and chucum extract, that the Maya used. The like with like approach has been shown to produce conservation repairs that are chemically and physically compatible with the original concrete and that perform well under the specific conditions of the tropical environment. The approach has been adopted as the standard conservation methodology at several major Maya archaeological sites, and the specific results of the conservation treatments have been monitored over periods of several years to evaluate the long-term performance of the conservation materials. The 14th major track of investigation has been the specific study of the Maya concrete in the context of the broader understanding of lime technology in the ancient Americas. The use of lime for construction purposes was not limited to the Maya, but was practiced by several other pre-Columbian civilizations, including the Aztec of central Mexico, the Zapotec of Oaxaca, the peoples of the Peruvian coastal region, and the mound builders of the southeastern United States. The comparative study of the lime technologies of these different civilizations has revealed specific similarities and specific differences that reflect the specific conditions of each region and the specific requirements of each civilization. The Aztec lime technology, which was practiced in the highlands of central Mexico from the 14th through the 16th centuries of the Common Era, produced a lime concrete that was used for the construction of the temples, the palaces, and the plazas of the Aztec capital Tenochtitlan, and the specific formulation of the Aztec concrete, which incorporated volcanic materials and specific organic additives, including the mucilage of the Megi cactus, reflected the specific geological and botanical conditions of the central Mexican highlands. The comparison between the Aztec concrete and the Maya concrete reveals the specific way in which each civilization adapted the basic lime technology to the specific conditions of its environment, using the specific raw materials and the specific additives that were available locally. The lime technologies of the pre-Columbian Americas, which were developed independently from the lime technologies of the Old World, and which produced materials with specific properties that are different from the properties of the Old World lime materials, demonstrate the specific creativity and the specific ingenuity of the pre-Columbian civilizations in the development of construction materials. The independent development of lime technology in the Americas, which parallels the independent development of lime technology in the Near East, in Europe, and in Asia, demonstrates that the discovery and the exploitation of the lime cycle is a convergent technological development that has been achieved independently by multiple civilizations in multiple parts of the world. The 15th major track has been the investigation of the specific role that the Maya concrete played in the urbanization of the Maya lowlands and in the specific demographic growth that characterized the classic Maya period. The Maya cities, which housed populations of tens of thousands of people in a tropical lowland environment that would otherwise support only a fraction of that population, were made possible by the specific capabilities of the Maya concrete, which provided the waterproof surfaces that collected the rainwater, the impermeable linings that stored the rainwater, the durable roads that connected the cities, and the solid platforms and structures that housed the population. The specific contribution of the Maya concrete to the urbanization process has been analyzed by demographers and urban planners who have estimated the specific population densities that the Maya cities could sustain as a function of the specific water storage capacity that the concrete-lined reservoirs provided. The analysis has shown that the population density of the Maya cities was directly correlated with the water storage capacity of the reservoir systems, and that the specific increases in population density that occurred during the Classic period were accompanied by specific increases in the water storage capacity that were achieved through the construction of additional reservoirs and through the improvement of the waterproofing of the existing reservoirs. The correlation between the population density and the water storage capacity demonstrates the specific dependence of the Maya urban population on the waterproofing properties of the Maya concrete and confirms the specific role of the concrete in making the Maya urbanization possible. The broader question of whether the Maya concrete was a necessary condition for the development of the Maya civilization, or whether the civilization could have developed without the concrete using alternative construction materials and alternative water management methods, is a counterfactual that illuminates the specific importance of the material for the civilization that produced it. The specific conditions of the Maya lowlands, particularly the absence of surface water and the porosity of the limestone bedrock, made the collection and the storage of rainwater an absolute necessity for the survival of the urban population, and the waterproof concrete was the specific material that made the rainwater collection and storage possible. Without the concrete, the Maya cities could not have stored the water that the population needed. The population could not have reached the densities that characterize the classic Maya cities, and the civilization could not have achieved the specific cultural, intellectual, and architectural achievements that make the Maya one of the most impressive civilizations in the ancient world. The Maya concrete was not merely a construction material, it was the foundation of the Maya civilization. The 16th major track of investigation has been the specific study of the lime concrete used in the Maya road surfaces, the SACBIOB, which provides a specific case study in the application of the Maya concrete technology to a demanding engineering problem. The SACB surfaces, which were required to resist the abrasion of foot traffic, the impact of the heavy rainfall, and the penetration of the vegetation roots, were subjected to a specific combination of mechanical, chemical, and biological stresses that required a specific concrete formulation that was different from the formulations used in the other applications. The analysis of the SACB concrete, which has been conducted at several SACB sites across the Maya lowlands, has revealed that the SACB formulation is characterized by a higher proportion of coarse aggregate than the other Maya concrete formulations, producing a material with a rougher surface texture and a greater resistance to abrasion. The SACB concrete also contains specific organic additives, though in lower concentrations than the reservoir concrete, that provide the waterproofing and the biological resistance that are needed for the durability of the road surface. The specific thickness of the SACB concrete surface, which is typically between 10 and 30 centimeters, is designed to provide the specific structural capacity that is needed to support the traffic load and to resist the penetration of the roots. The specific engineering of the SACB drainage system, which is designed to shed rainwater from the road surface and to prevent the accumulation of standing water on the road, is another aspect of the SACB engineering that demonstrates the specific hydraulic engineering capability of the Maya builders. The SACB surfaces are typically crowned with a slight convex curvature that directs the rainwater toward the edges of the road, where it is collected in drainage channels that carry it away from the road surface. The specific curvature of the SACB crown, which is typically approximately 5 to 10 centimeters over a road width of approximately 5 to 10 meters, is designed to provide the specific drainage gradient that is needed to shed the rainwater without creating excessive slopes that would impede the foot traffic. The survival of the SACB surfaces, which have been exposed to the tropical environment for more than 1,000 years, and which are still recognizable as road surfaces, despite the accumulation of soil and vegetation, demonstrates the specific durability of the Maya concrete formulation for the road application and provides additional evidence for the specific materials engineering capability of the Maya builders. The SACB surfaces, like the reservoir linings and the plaza floors, are specific examples of the Maya ability to adapt their concrete formulation to the specific requirements of each application, producing a range of materials that were optimized for the specific conditions and the specific stresses of each specific use. The 17th major track of investigation has been the study of the specific Maya concrete traditions at individual archaeological sites, aimed at identifying the site-specific variations in the concrete formulation and the site-specific innovations in the production and the application techniques that characterized the different Maya cities. The site-specific studies have revealed a significant degree of variation in the Maya concrete tradition, with different cities developing specific formulations and specific techniques that reflected the specific conditions and the specific requirements of each site. The specific concrete tradition at the site of Uxmal in the Puuc region of the northern Yucatan has been the subject of particularly detailed investigation, because the Puuc architectural tradition is characterized by exceptionally fine masonry and by the extensive use of lime concrete as a surfacing material. The Uxmal concrete, which has been analyzed using the full range of modern analytical techniques, shows specific features that distinguish it from the concrete of other Maya sites, including a particularly fine aggregate, a particularly compact microstructure, and a particularly high concentration of the specific organic additives that enhance the waterproofing and the durability of the material. The specific excellence of the Uxmal concrete, which is consistent with the overall excellence of the Puuc architectural tradition, demonstrates the degree to which the quality of the Maya concrete was determined by the specific skill and the specific knowledge of the local building tradition. The specific concrete tradition at the site of Copan, in the southeastern periphery of the Maya lowlands in modern Honduras, presents a contrasting case, because the Copan region has a different geological composition than the limestone lowlands of the Yucatan, with a greater abundance of volcanic materials that provided the Copan builders with a natural source of pozzolanic additives. The Copan concrete, which has been analyzed by researchers who have identified the presence of volcanic ash and volcanic tuff in the aggregate, shows higher concentrations of pozzolanic reaction products than the concrete from the limestone lowlands, demonstrating the specific adaptation of the Maya concrete tradition to the specific geological conditions of each region. The comparison between the Uxmal and the Copan concrete traditions illustrates the specific diversity of the Maya concrete tradition and the specific adaptability of the Maya builders to the specific conditions and the specific resources of each site. The diversity is itself a specific achievement of the Maya materials engineering tradition, demonstrating the capacity of the Maya builders to adjust their formulations and their techniques to the specific circumstances of each construction project, and to produce materials that were optimized for the specific conditions of each site. The 18th and final major track of investigation has been the specific analysis of the environmental footprint of the Maya concrete production in comparison with the environmental footprint of modern Portland cement production, an analysis that has produced specific quantitative estimates of the carbon emissions, the energy consumption, and the resource depletion associated with each production process. The analysis has confirmed that the Maya concrete production has a significantly lower environmental footprint than the Portland cement production on every measure, with carbon emissions that are approximately 30 to 50% lower, energy consumption that is approximately 40 to 60% lower, and resource depletion that is virtually zero because the raw materials for the Maya concrete are available in unlimited quantities in the limestone lowlands, and because the organic additives are derived from renewable plant sources that can be harvested sustainably. The specific analysis of the wear patterns on the Sacabee surfaces has provided information about the intensity and the patterns of the traffic that use the roads, with the most heavily worn sections corresponding to the approaches to the major cities and the intersections of the major routes. The wear patterns demonstrate that the Maya road system was actively used for centuries, and that the specific durability of the Sacabee concrete was essential for the continued function of the transportation network over this extended period. The integration of the specific environmental footprint analysis with the specific durability analysis produces a comprehensive picture of the long-term sustainability of the Maya concrete approach that is compelling in its specific implications for the modern construction industry. Everything we have discussed so far concerns the specific chemistry of Maya concrete, the specific additives that the Maya used, the specific properties that the material possesses, and the specific investigations that have been conducted to understand it. These matters are important, and they represent genuine advances in the understanding of one of the most fascinating construction materials in the ancient world. But beneath these specifics lies a deeper truth, a truth that concerns not just what the Maya concrete is, but what it means, what it tells us about the nature of materials engineering, about the relationship between a civilization and its environment, and about the specific way in which the knowledge of materials is developed, transmitted, and lost. The deeper truth is this: the Maya concrete is proof that the development of advanced materials is not the exclusive achievement of civilizations that possessed writing, that possessed formal scientific traditions, and that possessed the specific institutional structures that the modern world associates with technological innovation. The Maya, who did possess writing and who did possess a sophisticated intellectual tradition, did not develop their concrete through the specific processes of formal experimentation, of theoretical analysis, and of systematic optimization that characterize modern materials science. They developed it through the specific processes of empirical observation, of practical experimentation, and of intergenerational transmission that characterize the craft traditions of the pre-modern world. And the material that they produced through these processes is, in specific and measurable respects, superior to the materials that the formal scientific tradition has produced. This is not science fiction. This is a documented scientific fact. The specific durability of the Maya concrete in the tropical environment, its specific resistance to water penetration, its specific resistance to biological attack, and its specific resistance to the chemical dissolution that destroys other lime-based materials in the tropical conditions, are properties that the modern construction industry has not fully replicated using the methods and the materials of modern materials science. The Maya concrete, developed through centuries of empirical experimentation by craftsmen who did not possess the formal scientific knowledge that we now consider essential for materials engineering, is in specific respects superior to the products of the modern construction industry. Something is wrong with our assumption that the formal scientific method is the only pathway to the development of advanced materials. The Maya example demonstrates that the empirical method, the method of trial and error, of observation and adjustment, of incremental improvement over many generations, can produce materials of extraordinary sophistication and extraordinary durability, materials that rival and in some cases surpass the products of the formal scientific tradition. The lesson is not that the formal scientific method is unnecessary. The lesson is that the empirical method, when it is sustained over a long period, and when it is guided by the specific feedback of the material itself, can produce results that the formal method has not yet matched. The concept of traditional ecological knowledge, which refers to the specific knowledge of the natural environment and of the specific properties of natural materials that is accumulated by indigenous communities through centuries of observation and of interaction with their local environment, is directly relevant to the Maya concrete story. The specific knowledge that the Maya possessed about the specific plants, the specific minerals, and the specific procedures that were needed for the production of their concrete was a form of traditional ecological knowledge that was developed through the specific interaction of the Maya communities with the specific environment of the Maya lowlands. The knowledge was not abstract or theoretical. It was practical and specific, tied to the specific plants and the specific minerals that were available in the local environment and to the specific conditions of the local climate and the local geology. The loss of traditional ecological knowledge is one of the most significant and the most irreversible forms of knowledge loss that the modern world faces, because the traditional knowledge, which is typically transmitted through oral tradition and through practical demonstration, rather than through written texts, is vulnerable to interruption and to loss whenever the chain of transmission is broken. The Maya concrete knowledge, which was transmitted through the apprenticeship system and through the oral tradition of the Maya communities, was partially lost when the Spanish conquest disrupted the social and the institutional structures that had sustained the transmission, and the recovery of the knowledge has required the specific effort of the modern researchers who have collaborated with the indigenous Maya craftsmen to document and to preserve the remaining fragments of the tradition. The survival of specific elements of the Maya concrete tradition among the indigenous Maya communities of the modern Yucatan is one of the most hopeful aspects of the Maya concrete story, because it demonstrates that the traditional knowledge, while it has been diminished and fragmented by the disruptions of the colonial and the modern periods, has not been entirely lost, and that the specific knowledge that survives can be used as the foundation for the reconstruction of the tradition. The specific craftsmen who maintain the traditional knowledge of lime production and of organic additive preparation in the modern Maya communities are the living repositories of a knowledge tradition that is more than 2,000 years old, and the documentation and the preservation of their knowledge is one of the most urgent tasks in the archaeology of ancient materials. Let that sink in. The knowledge that the modern materials scientists are spending millions of dollars and years of effort to reconstruct through the laborious process of chemical analysis and experimental replication is knowledge that exists in specific and practical form in the minds and the hands of indigenous Maya craftsmen who learned it from their parents and their grandparents, in a chain of transmission that extends back to the builders of the ancient cities. The knowledge is there, embodied in the specific practices and the specific materials of the living tradition, waiting to be documented and to be studied and to be integrated into the modern understanding of materials science. The broader implications of the Maya concrete for the modern construction industry are significant and are becoming increasingly recognized by the materials science community. The specific properties of the Maya concrete, particularly its low carbon footprint, its use of locally available materials, its resistance to the specific conditions of the tropical environment, and its potential for sustainable production address specific challenges that the modern construction industry faces and that the conventional Portland cement technology does not adequately address. The carbon footprint of the Maya concrete production process is significantly lower than the carbon footprint of the Portland cement production process because the calcination of limestone at the temperatures used by the Maya, approximately 750 to 850 degrees Celsius, produces less carbon dioxide per unit of binding capacity than the calcination of the limestone and the clay that are used in the production of Portland cement, which requires temperatures of approximately 1450 degrees Celsius. The lower production temperature of the Maya process, combined with the carbonation of the lime during the setting process, which reabsorbs a portion of the carbon dioxide that was released during the calcination, produces a material with a net carbon footprint that is approximately 30 to 50% lower than the carbon footprint of Portland cement. The use of locally available materials in the Maya concrete, including the limestone that forms the bedrock of the construction site, the wood that grows in the surrounding forest, and the organic additives that are derived from the native plants, reduces the transportation costs and the transportation emissions that are associated with the production and the distribution of the construction material. The modern Portland cement industry, by contrast, relies on a centralized production system in which the cement is manufactured at large, capital-intensive plants and distributed over long distances to the construction sites, a system that generates significant transportation emissions and that is vulnerable to the disruptions of the transportation network. Let that sink in once more. An ancient civilization, working without the formal scientific knowledge of modern materials science, without the industrial infrastructure of modern manufacturing, and without the economic resources of modern economies, developed a construction material that is in specific and measurable respects more sustainable, more durable in its intended environment, and more environmentally appropriate than the construction material that the modern world uses for the majority of its construction. The Maya concrete is not merely an archaeological curiosity. It is a model for the development of the sustainable construction materials that the modern world urgently needs. The question of whether the Maya concrete technology can be scaled up to meet the demands of modern construction is one that is being addressed by materials scientists who are developing specific formulations and specific production procedures that adapt the Maya principles to the requirements of modern construction. The specific challenges that the scale-up faces include the development of standardized formulations that produce consistent, predictable properties, the identification of organic additive sources that can be produced in the quantities that modern construction requires, and the development of quality control procedures that ensure the reliability of the material in structural applications. The scale-up is not a simple task, because the Maya concrete tradition was a craft tradition that depended on the specific judgment and the specific skill of the individual craftsman, and the translation of this craft knowledge into the standard procedures of modern industrial production requires specific research and specific development that is still in its early stages. The concept of biomimicry, the design of materials and systems that are inspired by the specific strategies that biological organisms have developed to solve specific problems, is relevant to the Maya concrete story because the Maya, in their use of organic additives derived from specific plants, were exploiting the specific chemical properties that the plants had developed through millions of years of evolution. The polysaccharides, the proteins, the tannins, and the other organic compounds that the Maya used as additives were molecules that had been optimized by natural selection for specific biological functions, including the retention of water, the resistance to microbial attack, and the structural support of plant tissues. And the Maya, by incorporating these molecules into their concrete, were transferring the specific capabilities of the biological molecules to the inorganic matrix of the lime concrete. The biomimetic character of the Maya concrete has been recognized by modern materials scientists who are working to develop bio-inspired construction materials that incorporate organic additives derived from natural sources to improve the specific properties of the materials. The research into bio-inspired construction materials, which is one of the most active areas of modern materials science, draws directly on the Maya example, using the specific organic additives that the Maya identified, particularly the nopal mucilage and the chucum extract, as model systems for the development of new additive technologies that can be applied to modern lime concretes and to other cementitious materials. The specific concept of the self-healing material, which is a material that has the ability to repair damage to itself without external intervention, is one that has been identified in the Maya concrete and that has significant implications for the development of modern construction materials. The Maya concrete has been observed to develop a surface layer of calcium carbonate crystals that fills small cracks and pores in the concrete surface, a process that is promoted by the specific organic additives in the concrete, and that effectively heals the minor damage that the material sustains during its exposure to the environment. The self-healing property of the Maya concrete, which is comparable to the self-healing property that has been identified in Roman concrete, is a specific feature that contributes to the extraordinary durability of the material, and that provides a model for the development of self-healing construction materials for the modern construction industry. The broader significance of the Maya concrete for the field of sustainable construction is becoming increasingly recognized as the urgency of the climate crisis drives the search for construction materials and construction methods that are less carbon intensive than the Portland cement-based systems that dominate the modern industry. The specific advantages of the Maya concrete approach, which include the lower calcination temperature, the carbon reabsorption during the carbonation process, the use of locally available materials, and the potential for the use of renewable organic additives, address the specific challenges that the sustainable construction movement faces, and the Maya example provides a specific precedent and a specific inspiration for the development of the sustainable construction materials that the future requires. The relationship between the Maya concrete tradition and the modern concept of appropriate technology, which refers to technology that is designed to be compatible with the specific economic, social, and environmental conditions of the community that uses it, provides a framework for understanding the specific value of the Maya concrete in the context of modern sustainable development. The Maya concrete, which is produced from locally available materials using low-energy production methods and which is adapted to the specific conditions of the tropical environment, is an example of appropriate technology in its purest form, a technology that is specifically designed to meet the specific needs of the specific community that uses it, using the specific resources that are available in the specific environment of that community. The concept of appropriate technology is particularly relevant to the developing countries of the tropics, where the specific conditions of the local environment, the high temperatures, the high humidity, and the heavy rainfall pose specific challenges for the construction industry, and where the specific economic conditions, the limited financial resources, the limited industrial infrastructure, and the limited availability of imported materials constrain the specific construction methods and the specific construction materials that can be used. The Maya concrete, which was developed specifically for the tropical environment and which uses only locally available materials, addresses the specific challenges and the specific constraints of the tropical developing countries in a way that the imported Portland cement technology does not. The specific applications of the Maya concrete technology in the modern developing world include the construction of low-cost housing, the construction of water storage facilities, the repair and the restoration of historic buildings, and the construction of community infrastructure, including roads, plazas, and drainage systems that uses the specific materials and the specific methods of the Maya tradition. The specific projects that have been implemented using the Maya concrete technology have demonstrated the feasibility and the cost-effectiveness of the approach, and have shown that the Maya concrete can provide a durable, affordable, and environmentally sustainable construction material for the communities of the tropical lowlands. The specific collaboration between the modern materials scientists and the indigenous Maya communities in the development and the application of the Maya concrete technology is one of the most positive aspects of the Maya concrete research, because it recognizes the specific value of the traditional knowledge that the indigenous communities possess, and because it provides a model for the integration of traditional knowledge and modern science in the development of sustainable technologies. The collaboration has been conducted on a basis of mutual respect and mutual benefit, with the modern scientists contributing the specific analytical techniques and the specific theoretical frameworks of modern materials science, and the indigenous craftsmen contributing the specific practical knowledge and the specific experiential understanding of the traditional materials and methods. The broader significance of the collaboration between the modern scientists and the indigenous craftsmen is that it demonstrates the specific value of the traditional ecological knowledge that the indigenous communities possess, and that it provides a model for the preservation and the application of this knowledge in the modern world. The traditional knowledge of the indigenous Maya communities, which includes not only the specific knowledge of the concrete production, but also the specific knowledge of the local plants, the local minerals, the local climate, and the local ecology, is a resource of enormous value for the development of sustainable technologies that are adapted to the specific conditions of the tropical environment, and the collaboration between the modern scientists and the indigenous craftsmen is the specific mechanism by which this value can be realized. The question of what specific knowledge the Maya possessed about the relationship between the specific formulation of their concrete and the specific properties of the resulting material is one that connects the Maya concrete story to the broader question of the nature of empirical knowledge in the pre-modern world. The Maya, as we have noted, did not possess the specific scientific knowledge that would have allowed them to understand the chemistry and the physics of their material at the molecular level. They did not know the chemical formulas. They did not know the names of the specific compounds. They did not have the analytical instruments that would have allowed them to observe the microstructure or to measure the specific mechanical properties. And yet they produced a material with specific, measurable properties that are superior to the properties of the basic lime concrete from which it was derived. The specific knowledge that the Maya possessed was practical knowledge, knowledge of the specific relationships between the specific actions that they took and the specific results that they obtained. They knew that the addition of chucum extract made the concrete more waterproof. They knew that the addition of nopal mucilage made the concrete easier to work and harder when it dried. They knew that the specific temperature of the kiln affected the quality of the quicklime. They knew that the specific aging of the lime putty improved the workability and the durability of the concrete. They knew these things not because they understood the underlying chemistry, but because they had observed the relationships through centuries of practice, and because they had transmitted observations from one generation to the next through the specific mechanisms of the craft tradition. The specific form of the Maya knowledge, which was practical rather than theoretical, embodied rather than abstract, experiential rather than analytical, is a form of knowledge that the modern world has tended to undervalue and to overlook in favor of the theoretical, abstract, and analytical knowledge that is produced by the formal scientific tradition. The Maya concrete story demonstrates that the practical form of knowledge can produce results that are, in specific and measurable respects, superior to the results that the formal scientific tradition has produced, and the demonstration challenges the modern assumption that the formal scientific tradition is the only or the most effective pathway to the development of advanced materials. The specific value of the practical knowledge tradition is that it is directly connected to the specific conditions and the specific materials of the local environment, producing knowledge that is immediately applicable to the specific problems that the local community faces. The formal scientific tradition, by contrast, produces knowledge that is general and abstract, applicable to a wide range of conditions and materials, but not specifically adapted to the conditions and the materials of any particular environment. The Maya concrete tradition, which produced a material that was specifically adapted to the conditions of the tropical lowlands, is an example of the specific advantages of the practical knowledge tradition, advantages that are particularly evident in the specific environments and the specific conditions for which the formal scientific tradition has not developed specific solutions. The specific question of what the Maya concrete tradition can teach the modern world about the development of sustainable construction materials is one that is becoming increasingly urgent as the climate crisis intensifies and as the need for the reduction of the carbon emissions of the construction industry becomes more pressing. The specific lessons that the Maya concrete tradition offers include the specific use of locally available materials, which reduces the transportation emissions and the transportation costs of the construction process. The specific use of organic additives derived from renewable plant sources, which provides an alternative to the synthetic chemical additives that are currently used in the modern construction industry. The specific adaptation of the material formulation to the specific conditions of the local environment, which produces a material that is optimized for the specific challenges that the environment presents, and the specific use of the lime cycle as the basic chemical process of the concrete production, which produces a material with a lower carbon footprint than the Portland cement that dominates the modern construction industry. The specific research programs that are currently being conducted to develop modern construction materials based on the Maya concrete principles include programs at universities in Mexico, in the United States, in Europe, and in other parts of the world, and the specific results of these programs have demonstrated the feasibility and the promise of the Maya concrete approach for modern applications. The specific materials that have been developed include lime nopal concretes for the repair and the restoration of historic buildings, lime chukum waterproofing systems for the construction of water storage facilities in the tropical developing countries, and lime pozzolan concretes that combine the environmental advantages of the lime binder with the structural capabilities of the pozzolanic additives. The specific economic analysis of the Maya concrete approach for modern applications has shown that the Maya concrete materials are cost competitive with the Portland cement materials for specific applications, particularly the applications in the tropical developing countries where the local availability of the lime raw materials and the organic additives reduces the cost of the material, and where the specific durability of the Maya concrete in the tropical environment reduces the long-term maintenance costs. The economic competitiveness of the Maya concrete approach, combined with the environmental advantages and the cultural appropriateness of the approach, makes the Maya concrete a promising alternative to the Portland cement for specific applications in the tropical developing world. The specific philosophical implications of the Maya concrete story for the modern world extend beyond the practical questions of construction materials and sustainability to touch on the fundamental question of the relationship between human civilization and the natural world. The Maya concrete tradition, which was developed from the specific natural resources of the Maya environment and which was adapted to the specific conditions of the Maya landscape, embodies a specific philosophy of construction that is fundamentally different from the philosophy that underlies the modern Portland cement tradition. The modern Portland cement tradition is based on the philosophy of standardization, of the production of a single universal material that can be used in any environment and for any application, regardless of the specific conditions of the local context. The Portland cement is produced from standardized raw materials using standardized production procedures, and is designed to meet standardized performance specifications that are independent of the specific conditions of the specific location where the cement will be used. The philosophy of standardization has been enormously successful in producing a material that is available in virtually every corner of the globe and that meets the specific structural requirements of the modern construction industry, but it has also produced a material that is not specifically adapted to the specific conditions of any particular environment, and that requires specific maintenance and specific protection to perform adequately in the specific conditions that each environment presents. The Maya concrete tradition, by contrast, is based on the philosophy of adaptation, of the development of a material that is specifically tailored to the specific conditions of the local environment, using the specific resources that the local environment provides. The Maya concrete is not a standardized material. It is a family of materials, each formulation adapted to the specific requirements of the specific application and to the specific conditions of the specific environment, using the specific raw materials and the specific additives that are available in the local ecosystem. The philosophy of adaptation produces materials that are optimized for their specific context, that perform better in their intended environment than a standardized material would perform, and that are produced from locally available resources using locally available energy, reducing the environmental and the economic costs of the material production. The contrast between the philosophy of standardization and the philosophy of adaptation is one of the most profound implications of the Maya concrete story for the modern construction industry, because it challenges the assumption that a single standardized material can provide the optimal solution for every construction problem in every environment. The Maya example demonstrates that the philosophy of adaptation, which produces materials that are specifically tailored to the specific conditions of each environment, can produce materials that outperform the standardized materials in their intended context, and the demonstration suggests that the modern construction industry could benefit from a greater emphasis on the development of locally adapted materials that are designed for the specific conditions of each region rather than from the continued reliance on a single, universal material. The specific question of what the Maya concrete tradition reveals about the nature of innovation in pre-modern societies provides a final perspective that connects the Maya concrete story to the broader themes that we have explored in this series. The Maya concrete tradition demonstrates that innovation in pre-modern societies was not the product of individual genius, as the modern great inventor narrative suggests, but the product of a collective, intergenerational process of empirical observation, practical experimentation, and knowledge transmission that extended over many centuries, and that involved the cumulative contributions of many individuals over many generations. The collective, intergenerational character of the Maya innovation process is fundamentally different from the individual, instantaneous character of the innovation process that is celebrated in the modern narrative of technological progress, in which specific inventions are attributed to specific individuals at specific moments. The Maya concrete was not invented by a single individual at a single moment. It was developed by many individuals over many centuries, each individual contributing a specific observation, a specific experiment, or a specific improvement to the collective body of knowledge that constituted the tradition. The specific innovations that produced the Maya concrete, including the specific organic additives, the specific production procedures, and the specific formulation adjustments for different applications, were the products of this collective process, and the specific authorship of each innovation is lost in the anonymity of the craft tradition. The recognition that innovation in pre-modern societies was a collective, intergenerational process rather than an individual, instantaneous event has important implications for the modern understanding of the nature of innovation and for the specific policies and institutions that modern societies use to promote and to support innovation. The modern innovation system, which is based on the specific concepts of intellectual property, of individual invention, and of market-driven development, may not be the only or the most effective system for the development of specific types of innovation. And the Maya example suggests that the collective, intergenerational model of innovation, in which knowledge is shared freely and developed incrementally over many generations, can produce results that are, in specific respects, superior to the results of the modern individual model. What does the story of Maya concrete mean for our understanding of the relationship between ancient knowledge and modern technology, between craft traditions and scientific traditions, and between the specific environmental conditions of a civilization and the specific materials that the civilization develops? The first implication is a recognition that the development of advanced materials is not limited to civilizations that possess the specific institutional structures of formal science, and that the empirical traditions of the pre-modern world produced materials of extraordinary sophistication and extraordinary durability. The Maya concrete, the Roman concrete, the Indian woot steel, and the other advanced materials of the ancient world were all developed through empirical traditions that relied on practical observation, on intergenerational transmission, and on the specific feedback of the material itself, rather than on the formal scientific analysis that the modern world considers essential for materials engineering. The recognition that the empirical tradition can produce materials of this quality challenges the assumption that the formal scientific tradition is the only pathway to advanced materials and opens the possibility that the empirical traditions of the indigenous communities may contain specific knowledge that is valuable for the development of modern materials. The second implication is a recognition that the specific environment of a civilization is not merely a constraint on its technology, but a resource that shapes and enriches the technology in specific and often unexpected ways. The Maya, working in the limestone lowlands of the Yucatan, developed a concrete that was specifically adapted to the specific conditions of the tropical environment, using the specific plants, the specific minerals, and the specific geological materials that were available in their environment. The Roman, working in the volcanic regions of the Mediterranean, developed a concrete that was specifically adapted to the specific conditions of the maritime environment, using the volcanic ash that was available in their environment. Each civilization developed a material that was optimized for its specific environment, and the specific features of each material reflect the specific resources and the specific challenges of the environment in which it was developed. There is a pause worth taking here. Consider the Maya craftsman, standing at the edge of a lime kiln in the tropical heat, watching the limestone convert to quicklime in the flames of the burning wood. He has been taught by his father how to judge the temperature of the kiln by the color of the flames. He has been taught which trees produce the best wood for the kiln. He has been taught which bark and which sap to add to the lime to make it stronger and more resistant to the rain. He has been taught how to slake the quicklime, how to age the lime putty, how to mix the concrete, and how to apply it to the surface so that it bonds properly and dries evenly. He does not know the chemical formulas. He does not know the names of the specific compounds that are formed during the calcination and the carbonation. He does not need to know them, because his knowledge is practical, encoded in the specific procedures and the specific judgments that he has learned through years of observation and of practice. His knowledge is sufficient to produce a material that will endure for more than 1,000 years in one of the most destructive environments on the planet. The third implication is a recognition of the urgent need to document and to preserve the traditional knowledge of indigenous communities, knowledge that is being lost at an accelerating rate as the traditional lifestyles and the traditional practices of the indigenous communities are disrupted by modernization, by urbanization, and by the globalization of the economy. The traditional knowledge of the indigenous Maya communities, which includes the specific knowledge of the organic additives and the specific production procedures of the Maya concrete tradition, is a resource of immense value for the development of modern sustainable construction materials, and the loss of this knowledge would be an irreparable loss for both the indigenous communities and for the modern world. The fourth implication is a challenge to the modern construction industry to learn from the ancient Maya example and to develop construction materials that are more sustainable, more environmentally appropriate, and more durable than the Portland cement concrete that currently dominates the industry. The specific properties of the Maya concrete which include a lower carbon footprint, a greater resistance to the specific conditions of the tropical environment, and a greater use of locally available materials, address specific challenges that the modern construction industry faces and the specific knowledge that the Maya developed through their centuries of empirical experimentation provides a specific model and a specific inspiration for the development of the sustainable construction materials that the modern world urgently needs. The fifth implication is a celebration of the ingenuity and the creativity of the Maya civilization, a civilization that developed through the specific resources and the specific challenges of its environment, a construction material that has outlasted the civilization itself, and that continues to provide shelter, to store water, and to inspire wonder more than 1,000 years after the cities that it built were abandoned to the jungle. The Maya concrete is a monument to the specific genius of the Maya civilization, a genius that expressed itself not only in the mathematical precision of the Maya calendar and the artistic beauty of the Maya stucco, but also in the practical ingenuity of the Maya materials, engineering tradition, a tradition that produced a material of extraordinary sophistication and extraordinary durability from the simple, abundant materials of the Maya environment. The sixth implication of the Maya concrete story concerns the relationship between the decline of the Maya civilization and the loss of the Maya concrete knowledge. The decline of the classic Maya civilization, which occurred between approximately 800 and 1000 of the Common Era, resulted in the abandonment of many of the major Maya cities and in the disruption of the social and the institutional structures that had sustained the Maya construction tradition. The specific causes of the Maya decline, which have been debated by scholars for decades, and which are believed to include a combination of environmental degradation, drought, warfare, and social collapse, are relevant to the Maya concrete story because the decline resulted in the interruption of the specific chain of transmission that had maintained the concrete knowledge over the centuries. The specific loss of the most advanced elements of the Maya concrete tradition, including the specific knowledge of the organic additives and the specific production procedures that produced the highest quality material, was a consequence of the disruption of the specialist class of master builders who possessed this knowledge. The loss was not total, because the basic knowledge of lime production survived in the indigenous Maya communities and was transmitted to subsequent generations through the oral tradition and through the practical demonstration that are the specific mechanisms of knowledge transmission in the craft traditions. But the most advanced knowledge, the specific recipes, and the specific procedures that produce the highest performance material was disproportionately concentrated in the specialist class and was disproportionately affected by the disruption of that class. The Spanish conquest of the Maya region, which occurred in the 16th century of the Common Era, inflicted a second, devastating blow to the Maya concrete tradition because the conquest disrupted the indigenous social structures, imposed new construction methods and new construction materials, and suppressed the indigenous cultural practices that had sustained the transmission of the traditional knowledge. The specific knowledge of the Maya concrete, which had been maintained in diminished form by the indigenous communities through the centuries that followed the classic Maya decline, was further diminished by the colonial disruption, and the fragments of the tradition that survive in the modern Maya communities represent only a small portion of the original knowledge. The seventh implication of the Maya concrete story concerns the specific concept of material culture. The idea that the specific materials that a civilization uses are not merely the products of the civilization, but are also the expressions of the civilization's specific values, its specific priorities, and its specific relationship with the natural world. The Maya concrete, which was produced from the specific resources of the Maya environment, using the specific knowledge of the Maya craftsmen, is an expression of the Maya material culture, a physical embodiment of the Maya understanding of the natural world and of the Maya relationship with the land that sustained them. The specific features of the Maya concrete, its use of locally available materials, its incorporation of organic additives derived from native plants, its adaptation to the specific conditions of the tropical environment, and its production through the specific labor of the Maya community, reflect the specific values of the Maya civilization, including the value of self-sufficiency, the value of environmental adaptation, and the value of the specific relationship between the community and the land. The Maya concrete is not merely a construction material, it is a material expression of the Maya worldview, a physical record of the specific way in which the Maya understood and interacted with the natural world that surrounded them. The recognition of the Maya concrete as an expression of the Maya material culture provides a perspective that enriches the understanding of the material beyond its specific chemical and mechanical properties, and that connects the study of the material to the broader study of the Maya civilization and its specific cultural achievements. The Maya concrete, understood as a material culture artifact, is as much a product of the Maya intellectual tradition as the Maya calendar, the Maya writing system, or the Maya astronomical tradition, and the study of the material provides specific insights into the Maya understanding of the natural world that are not available from any other source. The eighth implication concerns the specific value of interdisciplinary research in the study of ancient materials, and the specific contributions that different disciplines have made to the understanding of the Maya concrete. The Maya concrete research has involved the collaboration of archaeologists, who provide the specific historical and cultural context of the material, materials scientists, who provide the specific analytical techniques and the specific theoretical frameworks for the understanding of the material's properties, chemists, who provide the specific knowledge of the chemical reactions and the chemical compounds that are involved in the production and the degradation of the material, botanists, who provide the specific identification of the plant species that are the sources of the organic additives, and indigenous craftsmen, who provide the specific practical knowledge of the traditional production methods. The specific contributions of each discipline have been essential for the overall understanding of the material, and the integration of the contributions of the different disciplines into a comprehensive picture of the Maya concrete tradition has been one of the most productive aspects of the research. The archaeologists have provided the specific information about where the concrete was used, when it was produced, and what specific structures it was used to build. The materials scientists have provided the specific measurements of the mechanical properties, the microstructural features, and the chemical composition. The chemists have provided the specific identification of the organic additives and the specific mechanisms by which the additives improve the properties of the concrete. The botanists have provided the specific identification of the plant species and the specific knowledge of their distribution and their traditional uses. And the indigenous craftsmen have provided the specific practical knowledge that connects the analytical results to the specific production procedures and the specific experiential understanding of the material. The Maya concrete research provides a model for the interdisciplinary study of ancient materials that is applicable to other ancient material traditions, including the Roman concrete tradition, the Chinese ceramic tradition, the Indian metallurgical tradition, and the other traditions that we have explored in this series. The model demonstrates that the understanding of an ancient material requires the integration of multiple forms of knowledge from multiple disciplines, and that the specific contributions of each discipline are essential for the completeness and the accuracy of the overall understanding. The jungle reclaims everything. The roots of the ceiba trees push through the plaster of the plaza floors. The vines climb the walls of the temples and pry apart the stones. The rain falls, season after season, century after century, dissolving, eroding, carrying away the substance of the city. The jungle is patient. The jungle is relentless. The jungle does not forget that the land was its own before the Maya built upon it, and the jungle works slowly and steadily to take it back. And yet the concrete endures. Beneath the roots and the vines, beneath the soil and the leaf litter that have accumulated over the centuries, the white surfaces of the Maya concrete are still there, still intact, still waterproof, still performing the specific function for which they were made more than 1,000 years ago. The plaza floors, which collected the rainwater and directed it to the reservoirs, are still capable of shedding water. The reservoir linings, which held the water that sustained the city through the dry season, are still capable of retaining water. The wall plasters, which protected the stone structures from the chemical attack of the rain and the biological attack of the organisms, are still performing their protective function, still holding together, still resisting the specific forces that should have destroyed them centuries ago. The math is striking. More than 1,000 years of exposure to the tropical environment. Temperatures that routinely exceed 35 degrees Celsius. Annual rainfall that exceeds 1,500 millimeters. A wet season that lasts for 6 months and a dry season that lasts for 6 months, subjecting the material to repeated cycles of saturation and desiccation. Acidic rain, acidic soil, acidic groundwater, root penetration, fungal attack, bacterial colonization, insect boring, earthquake tremors, hurricane winds, and still the concrete holds. Still the surfaces are intact. Still the material resists the specific forces that the environment applies to it, forces that would have destroyed any ordinary lime concrete within a few decades. The Maya who made the concrete did not know that their material would outlast their civilization. They did not know that the cities they built would be abandoned, that the jungle would reclaim the land, that the specific knowledge of their concrete-making tradition would be fragmented and dispersed by the disruptions of the centuries that followed. They made the concrete because they needed it, because the specific requirements of their environment, the need for waterproof surfaces, the need for durable structures, the need for reliable water storage, demanded a material that could perform in the specific conditions of the tropical lowlands. They made the concrete well, better than they needed to, better than anyone expected, and the material has outlived the civilization that made it by more than 1,000 years. The specific knowledge of the Maya concrete tradition, the specific recipes, the specific procedures, the specific judgments of the craftsmen who produced it, has been partially lost and is being partially recovered. The chemical analyses and the experimental replications of the modern researchers are filling in the gaps that the centuries have created, and the collaboration with the indigenous Maya craftsmen who maintain the living tradition is providing the practical knowledge that the chemical analyses cannot supply. The recovery is incomplete. It may always be incomplete, but the specific knowledge that has been recovered is sufficient to demonstrate that the Maya concrete tradition was one of the most sophisticated materials, engineering traditions in the ancient world, and that the specific material that the tradition produced is one of the most remarkable construction materials in the history of human building. The concrete is still there, beneath the jungle, waiting to be studied and waiting to be understood. The white surfaces gleam where the archaeologists have cleared away the vegetation and the soil, revealing the specific material that the Maya made from the bedrock of their land, from the wood of their forests, and from the sap of their trees, a material that was born from the specific conditions of the Maya environment, and that has proven, through 1,000 years of exposure to those conditions, to be perfectly adapted to the specific challenges that the environment presents. The material is the message, the concrete is the text, and the text says that the Maya, working with the specific resources of their specific environment, achieved a level of materials engineering that the modern world is only beginning to appreciate. The jungle grows, the concrete holds, and the knowledge, ancient and fragile and precious, survives in the hands of the craftsmen and in the analyses of the scientists, waiting to teach the modern world what the Maya knew about the art of building with the earth. The white surfaces are the signature of the Maya cities, the visible expression of the specific material that made the Maya civilization possible. Every major Maya city was covered in a continuous skin of white lime concrete, a skin that gleamed in the tropical sun and that gave the cities their characteristic appearance, visible from miles away, as bright white forms rising above the green canopy of the jungle. The whiteness was not merely aesthetic, it was functional, reflecting the heat of the sun and keeping the buildings cool, shedding the rain and preventing the water from penetrating the stone, and providing a smooth, clean surface that was suitable for the application of the bright paints and the elaborate stucco decorations that adorned the facades of the temples and the palaces. The whiteness is fading now, covered by the green of the jungle and the brown of the earth, hidden beneath the centuries of soil and vegetation that have accumulated over the abandoned cities. But beneath the covering, the white surfaces are still there, still intact, still performing, still resisting the forces that have been working to destroy them for over 1,000 years. The surfaces are the testimony of the Maya craftsmen, the evidence of their specific knowledge and their specific skill, written not in words, but in the specific chemistry and the specific microstructure of the material itself. The concrete is patient as the jungle that covers it, and it will wait, as it has waited for over 1,000 years, for the hands that will uncover it, and the minds that will understand it. The material has a story to tell, a story about a civilization that built with the earth beneath its feet, that waterproofed with the sap of its trees, that engineered with the knowledge of its craftsmen, and that produced a material that has outlasted everything else that the civilization created, a material that is still here, still whole, still holding, still testifying to the specific genius of the people who made it. The concrete is a bridge between the ancient and the modern, between the specific knowledge of the Maya craftsmen and the specific knowledge of the modern materials scientists, between the specific challenges of the ancient tropical cities and the specific challenges of the modern sustainable construction movement. The bridge is built of limestone and of water, of quicklime and of tree sap, of the specific materials that the earth provides, and that the human mind transforms into the specific substances that the human community needs. The bridge is ancient, but it carries a message that is profoundly modern, that the earth provides everything that is needed for the building of a durable, sustainable, and beautiful civilization, if only we have the knowledge and the skill to use what the earth provides. The Maya knew this. They built their civilization from the bedrock beneath their feet. They waterproofed it with the sap of their trees. They colored it with the clay of their soil and the dye of their plants. They made it endure through the specific knowledge that they accumulated over centuries of observation and of practice. Knowledge that was transmitted from parent to child, from master to apprentice, across the generations of the Maya civilization. The knowledge was specific. The knowledge was practical. The knowledge was sufficient. And the material that the knowledge produced is still here, still holding, still enduring, still teaching the modern world what the Maya knew about the art of building with the earth. The modern world builds with Portland cement, a material that is strong and versatile, but that produces approximately 7 to 8% of the global carbon dioxide emissions, and that deteriorates in the tropical environment at a rate that requires constant maintenance and periodic replacement. The ancient Maya built with lime concrete, a material that is weaker in compression, but that produces a fraction of the carbon emissions, that endures in the tropical environment for over 1,000 years, and that can be produced from the materials that lie beneath the feet of every builder in the limestone lowlands. The comparison is not a simplistic argument for the replacement of Portland cement with Maya concrete. It is a recognition that the ancient Maya, working with the materials of their specific environment, solved a specific problem in a specific way that the modern world has not yet matched, and that the specific solution that the Maya developed contains specific lessons that the modern world can use. The lessons are specific. Use the materials that are available. Adapt the formulation to the environment. Learn from the specific properties of the specific plants and the specific minerals that the local ecosystem provides. Build with the earth, not against it. The Maya knew these lessons. They embodied them in the specific material that they made, in the white surfaces of their cities, in the waterproof linings of their reservoirs, in the durable floors of their plazas. The material is the lesson. The concrete is the teacher,